What if everything we thought we knew about the orbits of planets, stars, and galaxies was only part of the story? Beneath the surface of what we can see lies a hidden universe, where invisible forces and unseen masses twist space and time in ways that defy our traditional understanding of gravity. Welcome to the world of non-Keplerian orbits, where celestial bodies move in mysterious, unpredictable paths governed by dark matter, black holes, and other hidden entities. Get ready to uncover how these invisible forces shape the cosmos in ways that challenge everything we know about the universe. But before we continue, subscribe to the channel so you don't miss out on any of these videos. Non-Keplerian orbits. A term that sounds technical, maybe even dry at first glance, but hides a staggering revolution in our understanding of the universe. In school, we are taught Kepler's laws, the sacred rules describing how planets orbit stars in neat ellipses, how speeds change predictably, how everything is mathematically elegant and orderly. But what happens when the mass that's controlling the orbit isn't visible? When it isn't a star, or a planet, or anything we can point to? When the center of gravity is effectively a ghost? It shatters the comforting simplicity of classical astronomy. It drags us into a universe where unseen forces dominate, where dark objects, from black holes to perhaps something even stranger, are silently choreographing the movement of matter across cosmic distances. Non-Keplerian orbits are not just weird mathematical tricks. They are smoking guns pointing toward the deepest mysteries of existence: dark matter, black holes, and perhaps entire realms of physics we have yet to discover. To fully grasp this phenomenon, we need to first tear down our standard model of how orbits work. Johannes Kepler, in the 17th century, formulated his three laws based on painstaking observations of planetary motion, especially those made by Tycho Brahe. His laws describe ellipses, areas swept out over equal times, and the relationship between orbital periods and distances. And they work beautifully for simple systems where two bodies dominate the gravitational interaction, like Earth orbiting the Sun. But what happens when the mass isn't where it's supposed to be? Or worse, when the mass is spread out in ways that classical Keplerian models can't handle? What if the gravitational pull isn't coming from a single, discrete object, but from an entire cloud of dark matter? What if space-time itself is being twisted and warped by something invisible? Suddenly, the tidy, predictable ellipses of Kepler's laws unravel into strange, distorted paths. Bodies can orbit in ways that seem impossible by classical standards. They can spiral, bob, precess, or hover in complex, dynamic dances that look more like chaotic art than the clockwork perfection of old astronomy. And yet, these bizarre paths are real. They are happening right now, scattered across galaxies, from the centers of quasars to the lonely voids between star systems. Invisible masses aren't just a theoretical quirk. We know they exist. We infer them by their gravitational effects. Stars at the edges of galaxies, for instance, move faster than they should based on the visible mass alone. This was one of the first major clues pointing toward dark matter, a form of matter that neither emits nor absorbs light but exerts gravitational pull. Dark matter constitutes about 85% of the mass of the universe, yet we have never seen it directly. It's this invisible mass that creates countless non-Keplerian orbits, deforming the expected paths into unexpected ones. Think of the classic image of a planet orbiting a star, an elliptical path, slowing as it moves outward, speeding as it approaches the perihelion. Now imagine instead a small satellite being pulled erratically by a lumpy, unseen cloud of mass that stretches across light years. There is no single center of gravity. Instead, the pull comes from multiple directions at once, changing subtly as the invisible structures within the cloud shift. This satellite's path would look nothing like a neat ellipse. It would appear to jitter, wobble, spiral unpredictably, but underlying it all would be the cold, inexorable tug of unseen mass. Even in the regions around known black holes, we see evidence of non-Keplerian orbits. The orbits of stars near the supermassive black hole at the center of the Milky Way, Sagittarius A*, deviate slightly from pure Keplerian ellipses. Their paths are influenced not just by the mass of the black hole itself, but by surrounding clouds of dark matter, smaller black holes, and potentially even more exotic structures, like dense star clusters or remnants of disrupted systems. And here's where things get truly mind-blowing. In some models, the orbits around these invisible masses don't just warp in space, they warp in time. General relativity tells us that massive objects warp space-time, meaning that time runs differently depending on how deep you are in a gravitational well. Around extremely dense, invisible masses like black holes or compact dark matter clumps, an orbiting body's experience of time can differ radically from that of a distant observer. To someone far away, the orbit might appear to slow, to stretch, to behave bizarrely. To the object itself, the passage of time feels normal. This creates another layer of distortion atop the already non-Keplerian paths, a temporal distortion that adds to the spatial one. Scientists have even proposed that some of the most extreme non-Keplerian orbits could be signatures of entirely new physics. Imagine orbiting structures that are not only responding to gravity but also to dark energy, the mysterious force driving the accelerated expansion of the universe. In such a scenario, an orbit might decay not simply because of gravitational radiation, as in the case of merging black holes, but also because of the dynamic influence of an evolving cosmological constant. It sounds like science fiction, but it's a real, serious area of research. Non-Keplerian orbits could also serve as natural laboratories for testing the limits of Einstein's general relativity. Near an invisible mass like a black hole, the precession of an orbit, the way the closest point of the orbit slowly rotates around, deviates from Newtonian predictions. These deviations are tiny for most orbits, but near extremely dense invisible masses, they become huge. By studying these precessions carefully, we can test whether general relativity holds perfectly, or whether there are tiny cracks hinting at a deeper theory. The Event Horizon Telescope's imaging of the black hole in M87, and ongoing observations of Sagittarius A*, are beginning to give us direct data on these extreme environments. Already, we are seeing tantalizing hints that some orbits do not behave exactly as expected. Some stars near Sagittarius A* seem to move slightly differently than models predict, suggesting either additional unseen masses or new gravitational physics at play. But non-Keplerian orbits around invisible masses aren't limited to black holes and dark matter. There are even more exotic possibilities. Some theories propose that clusters of primordial black holes, ancient black holes formed in the earliest moments after the Big Bang, could be scattered across the universe, invisible except for their gravitational effects. If these clusters exist, they could distort the orbits of nearby objects in ways that no single-mass Keplerian model could explain. Another radical idea is the existence of boson stars, hypothetical objects composed of massive scalar particles, unlike anything in the standard model of particle physics. Boson stars could be completely invisible electromagnetically but extremely massive gravitationally. Objects orbiting them would exhibit non-Keplerian dynamics, subtly different from those orbiting a black hole. Detecting these differences could be our first clue to the existence of an entirely new form of matter. And then there's the even stranger prospect of dark matter substructures, clumps, filaments, or even halos of dark matter within galaxies, whose gravitational effects could create chaotic, shifting orbital paths for stars, planets, and even smaller dark matter clumps themselves. In these regions, non-Keplerian orbits would not be rare exceptions but the rule. Think about that for a moment, an entire hidden architecture of mass, shaping the movements of celestial bodies, and we can only map it indirectly, by tracing the bizarre paths of the visible matter caught in its invisible embrace. It's like trying to understand the layout of a city by watching the strange, winding routes taken by lost travelers. The implications for cosmic evolution are staggering. Non-Keplerian orbits mean that galactic structure, star formation, planetary system evolution, all may be deeply influenced by invisible masses whose presence we can only guess at. Even our own solar system may not be immune. Some researchers have proposed that distant, unexplained orbits like that of the hypothetical Planet 9 could be signs of a massive, unseen object tugging subtly on the orbits of known bodies, creating anomalies that standard models cannot explain. The existence of non-Keplerian orbits also forces us to reconsider the future trajectories of space exploration. If we want to send probes to the outer solar system, or to interstellar space, understanding the gravitational influence of invisible masses becomes crucial. A spacecraft could be thrown off course by an unseen dark matter clump or by the gravity well of a rogue black hole drifting through the void. And there's a final, chilling thought. If entire regions of space are dominated by invisible masses, then navigating between the stars becomes not just a matter of speed and endurance but of carefully plotting courses through a minefield of unseen gravitational dangers. A spaceship hurtling toward an unseen mass could be torn apart, or thrown wildly off trajectory before its instruments even registered the anomaly. Understanding non-Keplerian orbits around invisible masses isn't just academic. It's a necessary step toward mastering the ultimate frontier, the hidden architecture of the cosmos itself. Non-Keplerian orbits shatter the basic assumptions we inherit from classical mechanics. Johannes Kepler, centuries ago, set the stage for how we understand motion in space. Planets move in ellipses, with the sun at one focus. The closer you are to the mass, the faster you move, the farther you drift, the slower your orbit. Simple. Predictable. Comforting. But the universe, as it turns out, is under no obligation to be simple, predictable, or comforting. When the mass you orbit is invisible, when it exerts influence without illumination, the very concept of orbit starts to mutate into something stranger, something almost alien. Invisible masses don't play by the rules we grew comfortable with. They distort space in subtle, sometimes deceptive ways. Dark matter, black holes, and other exotic objects introduce complexities into orbital dynamics that traditional Keplerian models can't account for. Suddenly, we see stars orbiting seemingly empty regions of space. We track clouds of gas spiraling around what appears to be nothing. We map galaxies whose rotation curves refuse to fit Newtonian expectations. Each of these anomalies opens a deeper question: what is really out there, hiding behind the veil of perception? The most unsettling part is this: non-Keplerian orbits could be more common than Keplerian ones. Our solar system may be a tame exception rather than the rule. Across the cosmos, where dark matter outweighs visible matter 5 to 1, the architecture of motion dances to a tune that Kepler never heard. Let's peel back the layers. In standard orbital mechanics, two-body systems are relatively easy to predict. You know the mass of the two objects, you know their distance, and you can calculate their paths. Even complicated systems like the gravitational ballet of moons around the planet still generally obey Kepler's and Newton's old laws, if you account for perturbations. But when an invisible mass enters the equation, and when that mass warps space in ways that traditional physics can't cleanly describe, you get non-Keplerian behavior. For instance, imagine a spacecraft orbiting not a planet, not a star, but a point of dark matter. There is no light to follow, no visual confirmation of its presence, only the unwavering pull of gravity, steady and persistent. The craft's orbit may appear erratic compared to a classic elliptical path. Small deviations compound over time. The ship might precess, spiral, or oscillate unpredictably, depending on how the mass distribution behaves. Traditional assumptions fail. Every calculation becomes a battle between what should happen and what actually does. And dark matter isn't even the strangest culprit. Gravitational anomalies like naked singularities, hypothetical objects in which the singularity of a black hole is visible, could twist spacetime so violently that orbits around them wouldn't just be non-Keplerian, they'd be something almost beyond mathematics. An object could orbit a naked singularity in paths that resemble chaotic fractals more than circles or ellipses. A journey around such an entity might look like a mad scribble from afar, endlessly looping and shifting, never settling into a predictable pattern. This kind of non-Keplerian behavior isn't just theoretical. Observations of stellar orbits at the center of our own galaxy hint at it. The so-called S-stars, such as S2, follow paths around Sagittarius A*, our local supermassive black hole, that at first glance seem Keplerian. But closer examination reveals perturbations, deviations that cannot be fully explained without invoking relativistic effects, unseen masses, or possibly distributions of dark matter. These orbits dance in subtle, intricate ways, suggesting that the very center of our galaxy may host not just a single black hole, but a more complex gravitational environment shaped by invisible structures. Even on a galactic scale, non-Keplerian dynamics rear their head. The rotation curves of galaxies, that is, the way stars orbit at various distances from the center, don't fit the expected drop-off in velocity predicted by visible mass alone. Instead of slowing down at the edges, stars maintain high speeds, as if gripped by an unseen hand. Dark matter is the mainstream explanation, a vast halo enveloping the galaxy, adding the missing gravitational glue. But the presence of this halo radically alters the orbital dynamics of everything inside. Stars are not simply obeying the gravity of the mass they can see, they are responding to a hidden architecture sculpted by mass they will never touch, never burn, never illuminate. What's more, there are theories proposing that some of these invisible influences might not be simple dark matter clouds. They could be compact, exotic configurations of matter, primordial black holes, axion stars, or other theoretical constructs born in the high-energy chaos of the early universe. Objects orbiting such masses would trace non-Keplerian paths, weaving unpredictable, chaotic arcs that defy easy modeling. On even smaller scales, spacecraft near Earth have occasionally exhibited tiny anomalies in their orbits, the so-called flyby anomaly, where the trajectory deviates minutely but measurably during Earth flybys. Though not conclusively tied to invisible masses, these subtle deviations ignite suspicion. What if small concentrations of invisible mass, perhaps clumps of dark matter, reside even within our own solar neighborhood? What if non-Keplerian distortions are happening right now, closer to home than we dare imagine? In the realm of theoretical physics, the situation grows even stranger. Some models of dark matter propose that it is not smoothly distributed like a gas, but clumped into filaments, sheets, and voids on various scales. An object moving through these structures wouldn't experience gravity as a smooth, predictable force. Instead, it might feel a tug here, a slackening there, a twisting pulse of attraction at unexpected moments. Imagine navigating a vast, invisible ocean, buffeted by currents you cannot see or predict. Your course, your orbit, your destiny would be forever altered by a topology you cannot perceive. This has profound implications for interstellar travel. Any civilization attempting to navigate the galaxy would need not just a map of the stars, but a detailed chart of the invisible gravitational terrain. Without it, a ship could drift into regions where non-Keplerian forces dominate, where predictable paths become treacherous. A miscalculation could send travelers spiraling into unseen wells of gravity, lost in the cosmic dark. And the implications ripple even further. If non-Keplerian orbits are common, then our methods for detecting exoplanets, often based on observing the wobbles they induce on their host stars, could be subtly flawed. If a star's motion is influenced not just by its planets, but by unseen masses, then the signals we interpret as planets might sometimes be misleading. Entire catalogs of exoplanets could be haunted by ghosts of dark matter. Even more chillingly, non-Keplerian orbits around invisible masses could serve as signposts, not just for natural phenomena, but for advanced civilizations. Some have speculated that if extraterrestrial intelligences sought to hide megastructures or activities, they might cloak them near or within regions dominated by dark matter. There, gravitational distortions already confound simple observations. A cloaked habitat orbiting an invisible mass could remain undetected indefinitely, its presence masked by the very distortions that non-Keplerian mechanics introduce. The physics underlying all this remains a frontier. General relativity describes how mass and energy curve spacetime, dictating the motion of objects. But when the distribution of mass is complex, when invisible masses warp space in intricate, multidimensional patterns, the resulting motion defies neat equations. Numerical simulations, supercomputers churning through trillions of calculations, are often the only way to model these behaviors. And even then, the results can be baffling: strange precessions, chaotic spirals, stable yet unclassifiable orbits that exist in the twilight zone between order and chaos. Yet nature is often subtler than our best theories. Some models predict that dark matter could self-interact. That is, dark matter particles might collide and clump, rather than simply passing through each other. This could create dense, compact dark structures scattered through the cosmos. Objects orbiting these structures would move in ways that blend classical Keplerian behavior with new, emergent patterns, paths that stretch, compress, and sometimes invert compared to traditional expectations. Stars revolve around unseen centers, entire galaxies spin in defiance of the mass we can measure, and gravitational currents guide matter along hidden highways sculpted not by shining stars, but by shadows. To truly grasp non-Keplerian orbits, we must first abandon the comforting simplicity of Newton's apple and Kepler's ellipses. In regions where invisible masses dominate, objects do not merely respond to a single central body. Instead, they are pulled and twisted by a complex, often chaotic web of gravitational influences. A spacecraft in such a region wouldn't just orbit neatly, it might spiral unpredictably, oscillate between multiple centers of mass, or even hover in a ghostly balance of forces. These bizarre motions often arise around black holes, the ultimate invisible masses. Black holes, despite their terrifying reputation, can exert gravitational influence without emitting a speck of light. Astronomers have detected stars whipping around seemingly empty patches of space at impossible speeds, with their trajectories veering sharply, revealing the unmistakable presence of something massive and compact. These stars follow paths that traditional Keplerian calculations fail to predict, hinting at the strange dance dictated by the black hole's warped spacetime. But the phenomenon goes even deeper. Dark matter, that elusive substance that fills the universe like an invisible scaffold, also plays a crucial role in creating non-Keplerian orbits. Galaxies themselves are wrapped in vast halos of dark matter, massive structures that exert gravitational pull without any visible source. The stars orbiting within these galaxies move too fast at the edges, far faster than what can be explained by the visible mass alone. They don't slow down as they move outward, defying the basic logic Kepler gave us. Instead, they remain locked in a tight gravitational embrace with something unseen, hinting at a cosmic architect we have yet to fully understand. The deeper scientists probe into this mystery, the more it becomes apparent that the universe we see is only a thin layer over a much stranger, hidden reality. Consider the case of gravitational lensing, where light from distant galaxies is bent and distorted by invisible masses between them and us. These lenses reveal concentrations of mass so massive and yet so dark that their very existence seems almost like an act of cosmic deceit. The light's path curves not because of what we can see, but because of what remains hidden. In certain extreme environments, like near supermassive black holes at galactic centers, the complexity of orbits reaches new heights. Here, the gravitational field is so intense that even time itself warps and stretches. Objects attempting to orbit these monsters find their paths twisted into chaotic loops, tight spirals, and sudden shifts. A planet, a star, or even a spacecraft near such an invisible mass would experience not a simple, closed ellipse, but a constantly shifting and precessing orbit, shaped not only by gravity but by the very geometry of spacetime. And there are even stranger possibilities. Theoretical physicists have proposed objects known as boson stars, hypothetical constructs made entirely out of quantum fields rather than regular matter. These objects could be massive, compact, and completely invisible to traditional telescopes. If they exist, they would create complex gravitational wells that could trap objects in strange, unpredictable orbits, perhaps creating signatures we have yet to recognize. Complicating this picture further is the idea that some of the invisible masses may not be static at all. In dynamic environments like colliding galaxies, dark matter halos can interact, merge, and distort. As the underlying gravitational landscape shifts, so too would the orbits of the visible matter caught in their grip. Stars might be flung out into intergalactic space, planetary systems might be disrupted, and entire stellar nurseries could be twisted into strange, filamentary shapes. Even at smaller scales, invisible masses can have profound effects. Rogue black holes wandering through space without a host galaxy, could quietly pass near a star system, subtly altering orbits without leaving any obvious visible clue. A planet that once had a stable, circular orbit could find itself slowly spiraling inward, or slingshot outward, all because of the silent passage of an invisible monster. In our own Milky Way, astronomers suspect the existence of thousands, perhaps millions, of stellar mass black holes drifting silently. Each one a potential architect of chaos, each one capable of seeding non-Keplerian orbital patterns wherever they roam. These invisible masses could explain strange anomalies in stellar motions, unexplained tilts in planetary orbits, or mysterious gaps in star clusters. All of this paints a picture of a universe far wilder, far less orderly than we once imagined. While Kepler gave us a beautiful, clockwork model of planetary motion, the reality appears far closer to a shifting, hidden ballet orchestrated by forces we cannot directly see. Every invisible mass, every pocket of dark matter, every rogue black hole adds another thread to the tapestry of gravitational complexity. The implications stretch beyond mere curiosity. If humanity hopes to navigate the stars someday, understanding these non-Keplerian dynamics will be crucial. A spacecraft venturing beyond the safe confines of the solar system could find its trajectory altered by unseen masses, its course bent and twisted by gravitational fields it cannot detect in advance. Planning interstellar travel will demand not just knowledge of visible stars, but maps of invisible masses, ghost charts plotting the unseen geography of spacetime itself. Some theorists have even speculated that entire civilizations, if they exist elsewhere in the universe, might already harness or navigate these hidden gravitational landscapes. An advanced species might build their spaceports near stable Lagrange points created by invisible masses, or use the strange properties of warped orbits to sling themselves across the stars with minimal energy. But long before we dream of such mastery, we must reckon with the raw, bewildering complexity of what non-Keplerian orbits truly mean. They remind us that our intuition, built from life under one sun, around one visible mass, is dangerously limited. They warn us that the cosmos hides more than it reveals, that the very foundations of motion and gravity are laid over a substrate we can barely glimpse. The hunt for invisible masses continues with ever more sensitive instruments. New surveys map stellar motions with unprecedented precision, revealing subtle perturbations that hint at unseen companions. Gravitational wave observatories detect ripples in spacetime from black hole mergers, giving us indirect glimpses of the dark creatures shaping the universe. And space telescopes peer deep into galactic hearts, looking for the telltale signs of matter moving to a rhythm we cannot see. One of the greatest achievements in modern astronomy was the discovery of S2, a star orbiting the invisible supermassive black hole at the center of our galaxy. Its orbit, painstakingly mapped over decades, revealed both the enormous mass and the inescapable pull of Sagittarius A star. Yet even here, deviations from pure Keplerian motion have been detected, tiny wobbles, slight shifts, suggesting that other, smaller invisible masses may be lurking nearby, distorting the star's dance in ways we are only beginning to understand. In the coming decades, missions like the Nancy Grace Roman Space Telescope and the European Space Agency's Gaia Observatory promise to reveal thousands more non-Keplerian mysteries. By tracking the tiniest motions of stars, these missions could uncover invisible planets, rogue black holes, and concentrations of dark matter sculpting orbits in secret. Perhaps the most tantalizing possibility of all is that some non-Keplerian motions could betray the presence of truly exotic objects, things not made of ordinary matter at all, but of strange new forms of existence predicted by speculative physics. Objects made of pure dark matter, quantum condensates, or even remnants from other universes could imprint their gravitational signatures onto nearby bodies, offering cryptic clues to realities we have not yet imagined. The idea that invisible masses shape motion at every scale challenges our most basic notions of how the universe works. It forces us to accept that much of what matters most is hidden, that the visible stars are mere lanterns flickering against a far vaster, darker stage. And if the history of science teaches anything, it is that where mysteries cluster, discoveries soon follow. The secrets wrapped within non-Keplerian orbits may, in time, unlock not just new maps of the cosmos, but new chapters in the story of existence itself. Until then, every flicker of starlight, every anomalous drift, every unexpected spiral reminds us, the invisible still rules the visible, and the greatest forces we contend with are often those we can least see. But the phenomenon goes even deeper. Dark matter, that elusive and invisible component making up roughly 85% of all matter in the universe, fundamentally alters how objects move on galactic and even intergalactic scales. Unlike a black hole, which is concentrated into a single point, dark matter is thought to be diffusely spread throughout vast halos enveloping galaxies. It does not clump into stars, nor does it glow, nor can it be seen by any electromagnetic radiation. Yet its gravitational influence is undeniable, revealed through the stubborn refusal of stars to slow down as they orbit their galactic centers. In a normal Keplerian system, we would expect the outermost stars of a galaxy to move more slowly than the ones near the center, just like planets in the solar system move slower the farther they are from the Sun. However, observations show that in most galaxies, the outer stars move just as fast, or even faster, than the inner ones. This flat rotation curve defies the predictions made by visible mass alone. It suggests that something invisible is holding the galaxies together, something providing the extra gravitational pull required to prevent them from flying apart. That something is dark matter, and it is precisely because of it that many celestial bodies in the universe are locked in non-Keplerian orbits. Moreover, when we consider the gravitational lensing effects, the bending of light around massive objects, we find even more confirmation of the unseen. Entire clusters of galaxies act as cosmic lenses, distorting the images of even more distant galaxies behind them. These distortions reveal mass where there should be none, further strengthening the case for invisible structures dictating motion on cosmic scales. The true weirdness sets in when we realize that non-Keplerian orbits don't just exist on large scales. Even on smaller, more intimate cosmic stages, they can dominate. Consider binary star systems where one star is visible, and the other is a black hole or a neutron star. The visible star's orbit will deviate subtly but detectably from a simple Keplerian ellipse. It may precess, its shape may change over time, and its velocity may oscillate in ways that tell a story of an invisible companion pulling at it with relentless, unseen hands. Then there are the rogue planets, wandering the galaxy without a home star, possibly ejected by chaotic, non-Keplerian gravitational interactions early in their solar system's lives. These lonely worlds drift through interstellar space, sometimes captured temporarily by passing stars, only to be flung away again, victims of a gravitational dance that defies tidy, textbook definitions of orbit. Our very methods of detecting exoplanets hinge upon the tiny deviations they cause in their host star's motions. A star that wobbles, accelerates, or shifts its position ever so slightly may betray the presence of unseen planets tugging at it. These wobbles are inherently non-Keplerian. They result from the complex gravitational interplay of multiple bodies influencing one another in a cosmic ballet that rarely fits into perfect ellipses or simple predictions. And what about the future? As our instruments grow ever more precise, as we map the motions of stars and galaxies in unprecedented detail, we are beginning to detect even subtler anomalies. Tiny discrepancies between predicted and observed orbits that suggest even deeper layers of invisible influence. Some theories propose exotic forms of matter or even modifications to gravity itself, speculating that the strange orbits we see might not just be caused by unseen masses, but by new, undiscovered laws of physics. Quantum theories of gravity, for instance, suggest that at extremely large or small scales, gravity might not behave exactly as Einstein described. These tiny deviations could manifest as non-Keplerian behaviors that subtly warp orbits over millions or billions of years, leaving faint fingerprints for future astronomers to uncover. In truth, we are only beginning to peel back the first layers of a cosmic mystery that stretches far beyond our current understanding. Non-Keplerian orbits around invisible masses are not an oddity. They are a fundamental part of how the universe operates. Every star that moves too fast, every gas cloud that curves inexplicably, every light beam that bends in empty space, is whispering a message from the hidden structures that shape reality itself. Imagine, then, a spacecraft navigating one of these invisible landscapes. Without the visual cues of nearby planets or stars, navigation would rely solely on measuring minute gravitational shifts. Pilots would have to trust instruments that track phantom pulls, guiding them through a terrain defined by absence rather than presence. Their maps would be of gravity wells they could not see, with pathways and traps determined not by light, but by mass hidden in shadow. Now consider the psychological implications for a civilization developing in such a region. A species evolving under the dominion of an invisible gravitational web might develop entirely different senses, perhaps sensitive to gravitational gradients rather than light. Their sciences, their entire worldview would be shaped by the unseen forces that govern their cosmos. To them, the visible stars might seem almost irrelevant, mere distractions from the true skeleton of reality. The questions only deepen the further we dive. If non-Keplerian orbits are so common, could there be entire systems stabilized by invisible masses? Could hidden objects, dark planets, primordial black holes, rogue neutron stars, serve as anchors for entire worlds, unseen yet essential for their existence? Could life itself arise on planets orbiting the void? The possibilities stretch our imaginations to the breaking point, and they challenge the very core of our cosmic self-image. For millennia, humanity has taken comfort in the idea that what we see is what exists, that the shining stars mark the structure of reality. Non-Keplerian orbits destroy that illusion. They reveal a universe built not upon light, but upon hidden mass, upon gravitational ghostlands where the rules we learn from our solar system no longer apply. Yet within this unsettling realization lies a profound beauty. The universe is not simpler than we thought. It is infinitely richer, stranger, and more complex. Each orbit that defies Kepler's laws, each anomaly that hints at an invisible mass, is a doorway into deeper truths about the cosmos. It is an invitation to rethink, to rediscover, to reimagine the very foundations of existence. And so, when we gaze up at the stars and marvel at their beauty, we must also remember the vast, unseen architectures that bind them together. For it is in the shadows, in the gravitational whispers, in the non-Keplerian motions, that the true majesty of the universe reveals itself, silent, unseen, but irresistibly powerful. Entire clusters of galaxies act as cosmic lenses, distorting the images of more distant galaxies behind them in ways that cannot be explained by the visible matter alone. The degree of distortion allows astronomers to map the invisible mass distributions, painting eerie, ghostly blueprints of dark matter's colossal reach. These distortions are not random. They form coherent patterns, suggesting that dark matter is not scattered haphazardly but follows a structured, though unseen, architecture. Within this structure, stars, gas clouds, and even entire galaxies are bound to non-Keplerian motions dictated not by what can be seen, but by what can only be inferred. In even more extreme environments, such as near-binary black hole systems or inside dense galactic cores, gravitational fields become so tangled and overlapping that the traditional notion of an orbit becomes almost meaningless. Instead of following smooth ellipses, objects can be trapped in chaotic orbits that seem to flicker and stutter, occasionally ejecting them at tremendous speeds in gravitational slingshots, or pulling them into spiraling death plunges. These dynamics create energetic fireworks observable across the universe, high-energy jets, bursts of gamma rays, and gravitational waves rippling through spacetime itself. What's perhaps most shocking is that scientists have already begun to simulate entire galaxies with dark matter-driven, non-Keplerian dynamics, and those simulations match reality far better than models that ignore the invisible component. It means that what we see, the bright, shining galaxies, the swirling arms of spiral galaxies, the vast, majestic clusters of galaxies, are merely the luminous frosting atop a dark, gravitationally dominant cake. Every visible feature of the universe is sculpted by forces most of us will never directly perceive. As researchers probe deeper, new theoretical frameworks are being developed to explain these motions. Modified Newtonian dynamics, MOND, alternative gravity theories like TeVis, and even exotic concepts like emergent gravity all attempt to account for the weird behavior we observe. Yet despite all these efforts, dark matter remains the most compelling explanation, an unseen architect behind the grand cosmic design. Beyond galaxies and black holes, non-Keplerian orbits manifest in environments closer to home as well. Consider the Earth-Moon system, influenced not only by their mutual gravitation but also by the gravitational pull of the Sun, other planets, and even, in minuscule ways, by Jupiter's vast gravitational field. Space agencies exploit these complex gravitational environments using what are called low-energy transfer orbits, sometimes referred to as ballistic capture orbits. These paths allow spacecraft to drift slowly into orbit around distant bodies using minimal fuel, guided not by the classic two-body problem solutions of Kepler and Newton, but by the chaotic interplay of multiple gravitational sources. In essence, when multiple invisible or distant masses tug on an object simultaneously, the resulting path becomes unpredictable, convoluted, and beautifully complex. This realization is transforming not only our view of the deep cosmos but also the very way we design space missions. It suggests a future where we might sling spacecraft across the solar system and beyond using intricate gravitational dances, harnessing the hidden fabric of spacetime itself. Delving even deeper into theoretical realms, physicists have explored whether massive structures of dark matter could harbor systems analogous to planetary systems, where visible matter orbits unseen dark cores. If true, it means entire planetary systems could exist where the central star is not a star at all, but a dense clump of dark matter. Such systems would be almost impossible to detect with traditional telescopes, relying instead on indirect signs like gravitational microlensing events, where the dark object's mass momentarily magnifies the light from a background star. This opens a tantalizing possibility. There could be countless dark solar systems scattered across the universe, places where planets and perhaps even life orbit around masses completely invisible to our senses. The mind reels at the implications. Civilizations, if they exist there, might have evolved without ever seeing their central mass, living their entire existence under a dark sun. In the realm of black holes, the notion of non-Keplerian orbits becomes even stranger when we introduce the concept of relativistic precession. When an object orbits close to a massive black hole, general relativity predicts that its orbit will not remain fixed but will slowly rotate around the black hole over time. This phenomenon was first confirmed with Mercury's orbit around the Sun, but near a black hole, the effect is far more dramatic. The closer an object gets, the more spacetime itself is twisted by the black hole's rotation, an effect called frame dragging. In such warped environments, orbits can become so distorted that traditional ideas of up, down, inside, and outside lose meaning. In fact, around rapidly rotating black holes, known as Kerr black holes, particles can enter stable orbits that appear to hover near the event horizon itself, existing in a precarious balance between falling inward and escaping outward. These orbits are purely non-Keplerian, defined not by the simple gravitational pull of a visible mass, but by the warping of spacetime on an extreme level. The study of such orbits is not just theoretical. Observations of stars near Sagittarius A*, the supermassive black hole at the center of our galaxy, are providing real-world tests of general relativity under the most extreme conditions. The star S2, for example, has been tracked over decades, revealing subtle deviations from Keplerian motion that perfectly align with relativistic predictions. Every slight wobble, every tiny precession, every unexpected speed burst is a testament to the deeper, hidden rules that govern motion near invisible masses. This interplay between theory and observation, between invisible mass and visible motion, is one of the greatest scientific detective stories ever told. Every new measurement, every refined orbit, every unexplained anomaly peels back another layer of the cosmic onion, hinting at even deeper truths. Even gravitational wave astronomy, the newborn field that detects ripples in spacetime caused by massive objects merging, is opening new windows into non-Keplerian dynamics. When two black holes spiral inward toward collision, their paths are wildly non-Keplerian, losing energy to gravitational radiation and moving in increasingly rapid, tightening spirals until they smash together in a titanic burst of gravitational energy. Observing these events allows scientists to study motion and mass under conditions utterly inaccessible by any other means. And yet, even with all these breakthroughs, the truth is humbling: we are just scratching the surface. Non-Keplerian orbits around invisible masses hint at a universe far richer, far more mysterious, and far less intuitive than our ancestors ever imagined. The glowing cores, the bright edges of galaxies, and the luminous stellar arms are merely the visible tracings of a much larger, invisible scaffolding. We are like insects crawling along a spider web we cannot see, feeling only the vibrations and occasional glimpses of structure through indirect signs. Our familiar rules of orbital mechanics, though remarkably accurate within our solar system, are insufficient when applied to the grander stage of the cosmos. Further complexities arise when we consider modified theories of gravity, such as modified Newtonian dynamics, and theories involving extra dimensions, which attempt to explain non-Keplerian behaviors without invoking dark matter. These hypotheses propose that at extremely low accelerations, the laws of gravity themselves might change, causing objects to behave in ways that appear non-Keplerian to an observer still assuming Newtonian laws apply everywhere equally. While dark matter remains the leading explanation, the possibility that our understanding of gravity is incomplete introduces even more layers of mystery. If gravity behaves differently at cosmic scales, then non-Keplerian orbits might not just be the result of unseen mass. They might be direct evidence that the fundamental laws governing motion and attraction are stranger than anything we currently imagine. In addition to these theoretical frameworks, observational evidence continues to pile up, pushing our understanding further into unknown territory. Near the centers of galaxies, especially supermassive black holes such as Sagittarius A** at the center of the Milky Way, astronomers have tracked stars that execute bizarre, tight, high-speed orbits that deviate subtly from simple ellipses. These small deviations might initially appear negligible, but they carry profound implications. They hint at additional masses, perhaps clusters of smaller black holes, dark matter spikes, or even more exotic objects like boson stars, theoretical entities composed of ultralight particles behaving collectively like a single massive body. Boson stars, if they exist, would present another challenge to Keplerian expectations. Unlike traditional matter, the quantum properties of boson fields allow these objects to have diffuse boundaries and spread out mass distributions, leading to gravitational fields that cause orbiting bodies to behave in entirely unexpected ways. A star orbiting a boson star might find itself in a pseudo-stable trajectory, hovering between gravitational peaks and valleys, never settling into the neat, predictable path that Keplerian physics would dictate. The mathematics of these systems is mind-bending. Instead of simple equations linking orbital speed and radius, models must incorporate general relativity, quantum field theory, and in many cases, computational simulations so complex that they take weeks or months even on supercomputers. Tidal forces, frame-dragging effects caused by spinning masses, and gravitational perturbations from nearby objects all weave into the tapestry of non-Keplerian dynamics. Small changes in position or velocity can cascade into enormous divergences over time, creating orbits that appear chaotic, fractal, or even seemingly random to an outside observer. But randomness is an illusion. Beneath the apparent chaos, strict physical laws govern every motion, even if they elude our present grasp. This raises tantalizing possibilities. By studying non-Keplerian orbits closely, we might uncover not only the presence of dark matter and exotic compact objects but entirely new physics that could revolutionize our understanding of the universe. Astrophysicists have already begun to leverage the subtleties of non-Keplerian orbits as tools of discovery. By tracking the precise paths of stars orbiting invisible masses, they can estimate the mass, spin, and even the potential composition of the hidden objects. In some cases, apparent orbital anomalies could point to hidden planets around distant stars, or even rogue black holes wandering through interstellar space. Future missions, employing ultra-precise astrometry, the measurement of stellar positions and movements, could reveal thousands or millions more such invisible influences across the sky. If current projects like the Gaia mission, which is mapping billions of stars in our galaxy with unprecedented accuracy, fulfill their promise, we may soon possess a detailed gravitational map of the Milky Way, a map not just of visible stars and planets, but of dark matter clouds, isolated black holes, and perhaps even stranger phenomena lurking in the galactic night. Understanding non-Keplerian orbits is not just an academic exercise, it has profound implications for our future as a spacefaring civilization. Navigating through regions dominated by invisible gravitational anomalies would require new kinds of spacecraft propulsion, guidance systems, and predictive models. A probe attempting to explore the dense heart of the Milky Way or skirt the edges of a dark matter filament would need to anticipate forces beyond those exerted by visible bodies. The wrong calculations could doom a mission before it even began. Even on Earth, recognizing the possibility of non-Keplerian gravitational effects at microscopic levels could influence technologies in ways we can scarcely predict, from better GPS systems that account for dark matter's subtle pull to entirely new ways of generating energy or manipulating matter. The philosophical consequences are even deeper. If invisible masses dominate not only the structure but also the motion of the universe, then the visible cosmos, the stars, the planets, the galaxies we see, is only the surface of a far vaster, hidden reality. Our very existence, the rise and fall of civilizations, the cycles of life itself, may all be shaped by gravitational fields woven by masses we cannot see and may never fully understand. As we continue to probe these mysteries, it becomes increasingly clear that the age of Keplerian simplicity is over. We are entering an era where motion must be understood not through the lens of neat ellipses and predictable speeds, but through a dynamic, ever-shifting dance choreographed by forces invisible to the eye yet undeniable in their power. Non-Keplerian orbits are not the exception, they are the rule, and the cosmos is far stranger, and more wondrous, than we ever dared to believe. As we continue to unravel the structure of the universe, the study of non-Keplerian orbits helps to reshape our perception of space and time. The traditional understanding of orbiting bodies, where planets, moons, and artificial satellites follow regular, predictable paths, assumes a relatively simple universe governed by uniform laws. However, as we look deeper into the heart of the cosmos, it becomes clear that we live in a universe far more complicated than we ever imagined. One of the most intriguing discoveries in this field is the motion of stars and galaxies. While we can observe stars moving in predictable orbits around a galactic center, these orbits don't always align with the expected paths calculated by Newton's laws of gravitation. The stars at the outer edges of galaxies, in particular, show motion that cannot be explained simply by the mass visible in the galaxy. These stars move faster than expected, suggesting the presence of additional, invisible mass that is influencing their motion. This invisible mass is what we call dark matter, and its effects on the orbits of stars are one of the most significant pieces of evidence for its existence. But dark matter is not the only explanation for these non-Keplerian orbits. The behavior of objects near supermassive black holes offers another fascinating insight into how gravity can behave in ways we don't yet fully understand. Stars orbiting supermassive black holes at the centers of galaxies, for example, show motions that defy the predictions of classical orbital mechanics. These stars often travel in highly elliptical orbits, moving at incredibly high speeds. Some of these orbits are so tight that the stars experience gravitational forces far stronger than anything we would expect in our solar system. In these extreme environments, the effects of general relativity become much more significant, and the traditional Keplerian laws break down. These high-speed orbits reveal a deeper understanding of the fabric of spacetime, showing us how massive objects warp space in ways that create orbits which would be considered non-Keplerian in a classical sense. The closer an object is to a supermassive black hole, the stronger these relativistic effects become. Matter doesn't simply follow a neat elliptical path. Instead, it moves in ways that are dictated by the complex curvature of spacetime caused by the enormous gravitational pull of the black hole. While the study of stars near black holes has provided a wealth of information about non-Keplerian orbits, it's in the search for rogue planets that we see the potential for new, unexplored areas of research. Rogue planets are those that do not orbit a star and instead drift through the galaxy, often bound to no particular system. These planets may have formed around stars long ago, only to be ejected due to gravitational interactions or other forces, and now they wander the vast emptiness of space. The orbits of these rogue planets are even more difficult to predict because, unlike planets in established orbits, they are not anchored by the gravitational pull of a star. Instead, their motion is influenced by the massive bodies they encounter, such as black holes or other rogue planets. These encounters can drastically alter their trajectories, sending them on paths that are completely unpredictable from a traditional orbital mechanics standpoint. As we detect more rogue planets and study their movement, we may come to understand the true extent of the gravitational forces shaping the cosmos. Interestingly, recent discoveries have suggested that rogue planets might not be as rare as once thought. Some studies indicate that there could be as many rogue planets in the Milky Way as there are stars. This raises the possibility that our solar system itself might have once had rogue planets, or even that there are still unseen rogue worlds lurking at the edge of the solar system. If these planets are moving in non-Keplerian orbits, tracking them becomes an even greater challenge, and our understanding of planetary motion may need to be completely rethought. Another critical aspect of non-Keplerian orbits is the study of gravitational lensing. This phenomenon occurs when the gravity of a massive object, such as a galaxy or black hole, bends the light from objects behind it, creating distorted images. By studying the light from distant stars or galaxies that has passed through these gravitational lenses, scientists can infer the presence and distribution of invisible masses, such as dark matter. These observations offer a unique window into regions of space where traditional methods of detection fail. Gravitational lensing has allowed astronomers to map out the distribution of dark matter in galaxies, revealing its presence even in places where it would otherwise be invisible. The lensing effect provides direct evidence of the invisible mass affecting the orbits of distant galaxies and stars, further confirming the existence of dark matter and its role in shaping the universe. As technology advances and our ability to detect and analyze gravitational lensing improves, we will be able to map out the gravitational fields of more distant and faint objects, shedding new light on the hidden structures of the universe. In addition to dark matter, non-Keplerian orbits offer insight into the properties of dark energy, the mysterious force driving the accelerated expansion of the universe. While dark matter works to pull objects together, dark energy is thought to be responsible for pushing them apart. The interplay between these two forces is still not fully understood, but the study of non-Keplerian orbits may hold the key to unraveling the mystery of dark energy. One of the most profound implications of studying these unusual orbits is the realization that the universe is not static, nor is it as orderly as we once believed. Non-Keplerian orbits force us to confront the fact that the forces of gravity, space, and time behave in ways that are more complex and chaotic than we can currently comprehend. The search for invisible masses, whether they are rogue planets, dark matter, or more exotic entities, pushes the boundaries of our knowledge and challenges the very foundations of physics. As our tools and technology continue to improve, the next generation of telescopes and space probes will allow us to observe the universe with even greater precision. Instruments like the James Webb Space Telescope are already providing unprecedented views of distant galaxies, and future missions could unlock even deeper mysteries. The data from these missions will likely reveal new kinds of non-Keplerian orbits, leading to discoveries that we cannot yet even imagine. With these advancements, we will also need to develop new mathematical models and computational techniques to make sense of the increasingly complex interactions we observe. As we venture further into the cosmos, we may discover entirely new types of orbits, influenced by unknown forces and governed by laws of physics that are still hidden from our understanding. These discoveries will reshape our place in the universe, as well as our understanding of how galaxies, stars, and planets form, evolve, and interact. The quest to understand non-Keplerian orbits is more than a scientific endeavor. It is a journey that may redefine our fundamental understanding of the universe itself. We are only beginning to scratch the surface of the vast cosmic machinery that shapes the movements of stars, planets, and galaxies. By peering into the invisible realms of dark matter, rogue planets, and supermassive black holes, we are slowly uncovering the hidden forces that govern the very fabric of space-time. As we continue to explore these mysteries, one thing is clear: the universe is far stranger and more complex than we ever imagined. What was once thought to be simple gravitational dynamics is now revealed to be a rich tapestry of forces, objects, and phenomena that challenge everything we know. Each new discovery brings us closer to understanding the invisible forces shaping the cosmos, and in doing so, we come closer to answering some of the most profound questions about the nature of reality itself. As our understanding of the universe evolves, the study of non-Keplerian orbits also provides valuable insights into the dynamics of galaxy formation and evolution. These invisible forces, whether from dark matter or other undiscovered cosmic phenomena, play a key role in shaping the structure of galaxies, how they interact with one another, and how they evolve over time. In galaxies, stars are not the only objects that are affected by these mysterious forces. The interstellar medium, the vast expanse of gas and dust between stars, also follows complex paths determined by gravitational interactions. This medium, often invisible to the naked eye, is largely influenced by the gravity of unseen masses like dark matter and dark energy. The way gas clouds move within galaxies can reveal the gravitational landscape of these galaxies, helping astronomers track down the distribution of dark matter. When it comes to galaxy collisions, non-Keplerian orbits become even more fascinating. During such encounters, galaxies can distort in unexpected ways, with stars, gas clouds, and dark matter rearranging their paths. The gravitational pull of dark matter in particular can cause unusual orbital patterns that go beyond simple elliptical trajectories, further complicating the idea of traditional orbital mechanics. In a galaxy collision, gravitational forces don't just pull stars and matter toward each other. They can also affect the non-visible mass that is spread out across the galactic structure. Dark matter, which constitutes the majority of a galaxy's mass, often plays a hidden but crucial role in shaping the orbits of stars and gas during such events. As galaxies collide, the dark matter halos that surround them exert influence on the motion of objects far beyond what would be expected from visible matter alone. The result is a turbulent but highly structured dynamic system, where objects follow unpredictable orbits that stretch the boundaries of Keplerian dynamics. These kinds of galactic interactions are essential to understanding the broader behavior of galaxies. Even without seeing the invisible mass directly, the effects of its gravitational influence are clear. These invisible forces are responsible for the formation of the spiral arms in galaxies, the retention of gas in the galactic center, and the interactions that give rise to galaxy clusters. Without the presence of these unseen forces, galaxies would not hold together in the same way, and the universe as we know it would likely look very different. As we continue to observe distant galaxies, we are increasingly confronted with evidence of these non-Keplerian forces at work. The gravitational pull of dark matter has been detected through its impact on the motion of galaxies and their constituent stars. Astronomers use this data to estimate the total mass of a galaxy, and by extension, to map out the distribution of dark matter. However, dark matter is still far from being fully understood. It doesn't emit light or interact with electromagnetic forces in any direct way, making it nearly invisible to conventional detection methods. Yet its gravitational influence on non-Keplerian orbits remains undeniable. One of the most intriguing aspects of non-Keplerian orbits involves their connection to the phenomenon of gravitational waves. Gravitational waves are ripples in spacetime itself, predicted by Einstein's theory of general relativity and first observed by LIGO in 2015. These waves are generated when massive objects, like black holes or neutron stars, move in such a way that they distort the fabric of spacetime. The motion of these objects creates waves that propagate outward, much like the ripples caused by a stone thrown into a pond. When two black holes orbit each other, their gravitational fields create powerful disturbances in spacetime. As these black holes spiral closer together, their orbits become more elliptical, and the gravitational waves they emit become stronger. These kinds of orbits, driven by intense gravitational forces, represent a key area where non-Keplerian dynamics are on full display. Unlike the regular elliptical orbits predicted by Kepler's laws, the orbits of black holes in such systems are not simple or predictable. Instead, they are chaotic, influenced by the bending and warping of spacetime as described by general relativity. The study of gravitational waves, which are closely tied to non-Keplerian orbits, provides a new way to observe the universe. Traditional methods of observing stars and planets rely on electromagnetic radiation, such as visible light or radio waves. Gravitational waves, however, offer a completely different perspective on cosmic phenomena. By studying these waves, astronomers can detect events in the universe that would otherwise remain hidden, such as the merger of black holes or neutron stars. These discoveries provide further evidence of the strange and unpredictable orbits that occur in the most extreme regions of space. In fact, the study of gravitational waves has already revolutionized our understanding of non-Keplerian orbits, allowing us to observe phenomena that were previously undetectable. For example, the first detection of gravitational waves was the result of a collision between two black holes, which spiraled inward in an increasingly tight, non-Keplerian orbit before eventually merging. This event, which was observed in 2015, gave scientists a direct measurement of a non-Keplerian orbit in action, providing a wealth of information about the behavior of objects in such extreme conditions. As the study of gravitational waves continues to advance, we will gain even more insight into the dynamics of non-Keplerian orbits. These waves offer a unique window into the motion of massive objects that cannot be observed through traditional methods. The more we learn about gravitational waves, the better we will understand the behavior of orbits in the most extreme and invisible regions of the universe. Beyond gravitational waves, the concept of orbits around invisible masses also extends into the realm of theoretical physics, especially when considering the possibility of other dimensions or exotic matter. One of the most exciting possibilities in the realm of modern physics is the idea that the universe might have hidden dimensions that we cannot perceive directly. If these dimensions exist, they could have a profound impact on the behavior of objects in non-Keplerian orbits. Theories such as string theory suggest that additional spatial dimensions could be influencing the gravitational forces we observe. These extra dimensions could be responsible for creating the mysterious gravitational effects that lead to non-Keplerian orbits, particularly in the case of objects like black holes, where the curvature of spacetime is most pronounced. In such a model, the extra dimensions could alter the way that gravitational forces behave, leading to orbits that defy traditional predictions. Furthermore, if exotic matter such as phantom energy exists, it could have even more profound effects on non-Keplerian orbits. Phantom energy is a hypothetical form of energy that has negative pressure so extreme that it would cause the universe to expand at an ever-increasing rate. If such energy exists, it could warp space in ways that create even more unusual orbital patterns, potentially providing new insights into the nature of dark energy and its role in the accelerated expansion of the universe. As we look ahead, the discovery of these hidden forces and dimensions could open up a new era of space exploration and understanding. By observing how these invisible masses influence the orbits of celestial bodies, we might uncover entirely new laws of physics that could explain some of the greatest mysteries of the universe. The study of non-Keplerian orbits represents not only a challenge to our understanding of gravity and celestial mechanics, but also an opportunity to expand the boundaries of our knowledge. The invisible forces that shape the orbits of stars, planets, and galaxies are more than just curiosities. They are a window into a deeper, more complex universe than we ever thought possible. As our technology advances and our understanding of the cosmos deepens, we are on the brink of discovering new, unimaginable aspects of the universe that will continue to inspire wonder and awe for generations to come. As the hunt for invisible masses and non-Keplerian orbits continues, astronomers and physicists are increasingly turning to advanced computational models and simulations to unravel the mysteries of these phenomena. These models simulate the gravitational effects of unseen masses like dark matter, dark energy, and black holes in ways that would be impossible to replicate with simple observational methods. Through these simulations, we can begin to visualize how objects might behave under the influence of these invisible forces, providing valuable insights into the dynamics of non-Keplerian orbits. The complexity of these simulations is staggering. They involve modeling the interactions between vast numbers of particles, taking into account the gravitational effects of not only visible matter but also the elusive dark matter that permeates the universe. These simulations are run on supercomputers that can process billions of calculations per second, allowing scientists to test theories about the nature of gravity, dark matter, and other cosmic phenomena in a controlled environment. By comparing the results of these simulations with actual observational data, astronomers can refine their understanding of how non-Keplerian orbits work in practice. One of the most significant challenges in these simulations is accounting for the effects of dark matter and dark energy. These invisible substances do not interact with light or electromagnetic radiation, making them incredibly difficult to detect directly. However, their gravitational effects on the motion of visible matter are significant. Dark matter, in particular, is thought to account for roughly 85% of the mass of the universe, yet we can't observe it through traditional means. Instead, scientists infer its presence by examining the orbits of stars and galaxies, which behave differently than expected based on the gravitational influence of visible matter alone. One of the most striking observations related to dark matter is the way galaxies rotate. If we observe a galaxy, we can measure the speed at which its stars move around the galactic center. Based on the amount of visible matter, like stars, gas, and dust, in the galaxy, we would expect the stars on the outer edges of the galaxy to move more slowly than those near the center. However, this is not what we observe. Stars on the outskirts of galaxies are moving much faster than expected, indicating that there is additional, invisible mass providing extra gravitational pull. This discrepancy can only be explained by the presence of dark matter, which extends far beyond the visible edge of the galaxy, forming a halo that exerts gravitational forces on the stars within the galaxy. This results in a non-Keplerian orbital pattern, where the stars on the outer edges of the galaxy follow a much more constant speed, rather than slowing down as Kepler's laws would predict. The discovery of this anomaly was one of the key pieces of evidence for the existence of dark matter, and it continues to drive research into the role that invisible masses play in shaping the universe. Another important observation that suggests the existence of non-Keplerian orbits is the behavior of galaxy clusters. Galaxy clusters are groups of galaxies that are bound together by gravity, and they provide a natural laboratory for studying the effects of invisible masses. When scientists measure the speed at which galaxies are moving within a cluster, they find that the galaxies are moving much faster than would be expected based on the visible matter in the cluster. This again points to the presence of dark matter, which provides additional gravitational pull, keeping the galaxies from flying apart despite their high velocities. Moreover, the study of galaxy clusters also reveals an intriguing phenomenon known as the gravitational lensing effect. This occurs when the light from distant galaxies is bent around a massive object, such as a galaxy cluster, due to the intense gravitational field of the object. This bending of light is a direct result of Einstein's theory of general relativity, and provides a powerful tool for mapping the distribution of dark matter in the universe. By studying the way light is distorted as it passes through galaxy clusters, astronomers can create detailed maps of the invisible mass within these clusters, further confirming the existence of non-Keplerian orbits driven by dark matter. The implications of these findings extend far beyond the study of galaxies and galaxy clusters. Understanding the influence of invisible masses on orbital dynamics could also help to explain some of the more mysterious and unusual cosmic phenomena, such as the motion of objects near black holes. The supermassive black holes that reside at the centers of most galaxies exert an enormous gravitational pull, and their effects on nearby stars and gas clouds can result in orbits that seem to defy conventional gravitational laws. These orbits are often chaotic and unpredictable, but they follow the rules of general relativity, which accounts for the warping of spacetime in the presence of such massive objects. The most extreme examples of non-Keplerian orbits can be found around black holes, especially those in the process of accreting matter. When a black hole pulls in gas, dust, and even entire stars, the material forms a swirling disk around the black hole known as an accretion disk. The motion of objects within this disk is governed by the immense gravitational forces of the black hole, and the orbits of particles within the disk are far from Keplerian. Instead of following simple elliptical paths, particles in the accretion disk follow complex, non-Keplerian orbits that are influenced by both the black hole's gravity and the relativistic effects of spacetime curvature. In addition to the material in the accretion disk, the supermassive black holes at the centers of galaxies can also influence the motion of stars and gas clouds in their immediate vicinity. Some of these objects follow highly elliptical orbits that are shaped by the gravitational forces of the black hole, while others are ejected from the system entirely. These ejected objects, often referred to as hypervelocity stars, are flung out of the galaxy at incredibly high speeds, a phenomenon that cannot be explained by traditional Keplerian orbits alone. The study of these extreme cases of non-Keplerian orbits provides valuable insights into the behavior of matter under the influence of incredibly strong gravitational forces. By understanding how objects behave in the presence of black holes and other massive, invisible objects, we can learn more about the fundamental nature of gravity and space-time. Moreover, these studies also shed light on the role that invisible masses like dark matter play in shaping the dynamics of galaxies, stars, and other celestial bodies. The pursuit of understanding non-Keplerian orbits is still ongoing, and it is clear that there is much more to learn. With the advent of new technologies, such as the James Webb Space Telescope and advanced gravitational wave observatories, we are poised to make even more groundbreaking discoveries in the coming years. These discoveries could open up new areas of research into the nature of invisible masses and the forces that govern their behavior. As we continue to explore the universe, we are certain to encounter even more strange and puzzling orbital patterns that challenge our current understanding of gravity and celestial mechanics. At the heart of this exploration lies the realization that our universe is far more complex and mysterious than we ever imagined. The invisible forces that shape the orbits of stars, galaxies, and black holes reveal a universe that is full of hidden dynamics, where forces that we cannot directly observe have a profound impact on the structure and behavior of the cosmos. As we continue to unravel these mysteries, we move closer to understanding not just how the universe works, but why it works the way it does. The study of non-Keplerian orbits serves as a reminder that the universe is filled with hidden wonders, forces, masses, and phenomena that challenge our understanding and invite us to explore further. Whether through the study of galaxy dynamics, the search for dark matter, or the investigation of black holes and gravitational waves, these invisible forces are shaping the universe in ways we are only beginning to comprehend. The more we learn, the more we realize that the cosmos is not just a place of stars and planets, but a realm of invisible forces, unseen masses, and mysteries yet to be solved. As the search for these invisible forces deepens, scientists are exploring new theoretical frameworks to explain the observations that challenge traditional understanding. One such framework is the concept of modified gravity theories, which attempt to explain the behavior of galaxies, black holes, and other cosmic phenomena without relying solely on dark matter. These theories, such as modified Newtonian dynamics, and Tevis tensor, vector, scalar gravity, propose that gravity itself might behave differently at large scales or in the presence of extreme gravitational fields. While these theories offer an alternative perspective, the overwhelming evidence supporting the presence of dark matter and its effects on non-Keplerian orbits makes them a more controversial avenue of research. Nonetheless, exploring these theories is crucial, as they push the boundaries of our understanding and challenge the status quo. The beauty of science lies in its ability to adapt and evolve when faced with new data, and modified gravity theories offer an intriguing way to rethink the dynamics of the universe. By testing these models against observational data, scientists can refine their understanding of the laws of physics and potentially unlock new explanations for the unseen forces at work. In the search for invisible masses, gravitational lensing remains one of the most powerful tools at astronomers' disposal. Gravitational lensing occurs when the light from a distant object, such as a galaxy or star, is bent by the gravitational field of a massive object located between the source and the observer. This effect allows astronomers to observe objects that would otherwise be too far or too faint to detect, and it also provides a unique way to map the distribution of invisible matter. By studying how light is distorted as it passes through galaxy clusters, astronomers can create detailed maps of the dark matter within those clusters, offering crucial clues about the nature of non-Keplerian orbits. One of the most famous instances of gravitational lensing is the phenomenon known as Einstein's ring. When a perfectly aligned massive object, such as a galaxy cluster, lies between a distant source and an observer, the gravitational field of the cluster can bend and focus the light from the background object, creating a ring-like structure around the lensing object. This phenomenon not only provides direct evidence of the existence of invisible matter but also gives scientists a glimpse into the intricate relationship between mass, gravity, and light. Einstein's ring is a testament to the mind-bending effects of gravity, and it serves as a reminder of the vast, unseen forces that shape our universe. Another fascinating aspect of non-Keplerian orbits involves the study of rogue planets. These are planets that do not orbit a star but instead wander freely through the galaxy, often captured by the gravitational influence of a massive object such as a black hole or a nearby star. Rogue planets are prime candidates for exhibiting non-Keplerian orbital behaviors, as their motion is not bound to a stable, predictable orbit around a central star. Instead, their paths are influenced by the gravitational forces of nearby objects, leading to highly erratic orbits that defy conventional Keplerian laws. Rogue planets are difficult to detect because they do not emit their own light and are often too faint to observe directly. However, through the study of gravitational microlensing, scientists have been able to identify a few candidates. Gravitational microlensing occurs when the gravitational field of a rogue planet bends the light from a background star, briefly magnifying its brightness. This effect, although fleeting, allows astronomers to detect the presence of otherwise invisible planets and gain insight into their orbital characteristics. Studying rogue planets can provide valuable information about the behavior of non-Keplerian orbits and help scientists understand the role that invisible masses play in the formation and motion of planetary bodies. The relationship between black holes and non-Keplerian orbits is also an area of intense research. Supermassive black holes, found at the centers of most galaxies, exert immense gravitational forces on their surroundings, influencing the motion of stars, gas clouds, and even entire galaxies. The orbits of objects near black holes can be highly complex, as they are not governed by simple elliptical trajectories as described by Kepler's laws. Instead, objects in close proximity to black holes often follow spiraling, non-Keplerian orbits that gradually decay as they lose energy and spiral inward toward the event horizon. This process, known as accretion, is central to the formation of the accretion disk around black holes. The material in the accretion disk moves in chaotic, non-Keplerian orbits due to the intense gravitational field of the black hole. As the material spirals inward, it heats up, emitting radiation that can be detected by telescopes. This radiation provides valuable information about the behavior of matter in extreme gravitational environments and offers a glimpse into the inner workings of black holes. In some cases, black holes can also eject material in powerful jets that travel at nearly the speed of light. These jets are often observed in active galactic nuclei (AGN), where the supermassive black hole at the center of a galaxy is actively accreting material. The process by which material is ejected from the black hole is not fully understood, but it is believed to be related to the complex dynamics of non-Keplerian orbits in the accretion disk. The ejection of material may occur when the forces within the disk become unbalanced, causing the material to be flung outward in a jet-like stream. The study of non-Keplerian orbits around black holes also sheds light on the nature of spacetime itself. According to Einstein's theory of general relativity, massive objects like black holes warp the fabric of spacetime, causing the orbits of nearby objects to follow curved paths. In extreme cases, the curvature of spacetime around a black hole can cause objects to follow highly distorted orbits that are far from the simple ellipses predicted by Kepler's laws. These warped orbits are not just a theoretical concept. They have been observed in the motion of stars and gas clouds near the supermassive black hole at the center of our galaxy, Sagittarius A star. The behavior of non-Keplerian orbits near black holes also provides crucial insights into the structure of spacetime at the event horizon, the boundary beyond which nothing, not even light, can escape. The study of these orbits helps scientists understand how matter behaves under the most extreme conditions, offering valuable clues about the fundamental nature of gravity, quantum mechanics, and the structure of the universe itself. While much of the research into non-Keplerian orbits is theoretical, new technologies are allowing astronomers to observe these phenomena more directly. The development of gravitational wave detectors, such as LIGO and Virgo, has opened a new window into the study of non-Keplerian orbits. Gravitational waves are ripples in spacetime caused by the acceleration of massive objects, such as merging black holes or neutron stars. By detecting these waves, scientists can gain insights into the dynamics of objects that produce them, including those involved in non-Keplerian orbits. The detection of gravitational waves from merging black holes, for example, has provided a wealth of information about the behavior of objects in extreme gravitational environments. These observations confirm that the orbits of black holes in close binary systems can follow highly elliptical, non-Keplerian paths, with the black holes gradually spiraling toward one another before merging in a burst of gravitational radiation. This discovery has not only deepened our understanding of black hole physics but also validated the predictions of general relativity, which describes how massive objects warp spacetime and influence the motion of nearby bodies. Gravitational wave astronomy is still in its early stages, but it promises to revolutionize our understanding of non-Keplerian orbits. As detection technology improves and more events are observed, scientists will be able to probe deeper into the mysteries of invisible masses and the complex dynamics of the universe. Gravitational waves provide a unique way to study the motion of objects that cannot be observed through traditional means, offering a direct glimpse into the invisible forces that shape our universe. As we continue to explore the cosmos, the study of non-Keplerian orbits will remain a central focus of astronomical research. Whether through the observation of galaxy dynamics, the study of rogue planets, or the detection of gravitational waves, scientists are continually uncovering new insights into the behavior of objects under the influence of invisible masses. These discoveries not only expand our understanding of gravity and the fundamental forces of nature but also challenge our perceptions of the universe itself. The more we learn about non-Keplerian orbits, the more we realize that the universe is far more mysterious and complex than we ever imagined. From the unseen forces of dark matter and dark energy to the strange and chaotic behavior of objects near black holes, the cosmos is filled with hidden dynamics that continue to fascinate and inspire. As we unlock the secrets of these invisible forces, we come closer to answering some of the most profound questions about the nature of the universe and our place within it. One particularly striking use of gravitational lensing is in the study of galaxy clusters. When light from background galaxies passes through a galaxy cluster, it gets bent and magnified, creating arcs and multiple images of the same object. The patterns of these distortions provide a detailed map of the gravitational potential of the cluster, highlighting areas where dark matter must be present to account for the observed effects. These gravitational maps consistently show far more mass than can be explained by the visible stars and gas alone, offering yet another powerful confirmation of invisible mass influencing non-Keplerian orbits. Moreover, gravitational lensing allows scientists to study extremely distant galaxies, sometimes looking billions of years into the past. This ability not only opens a window to the early universe but also gives insight into how dark matter influenced the formation and movement of galaxies from the very beginning. Observations of these lensed galaxies show signs of rotation curves and orbital dynamics that differ significantly from what would be expected in a purely Newtonian system, further supporting the reality of non-Keplerian influences. Aside from dark matter, another invisible agent causing non-Keplerian behavior is the presence of intermediate mass and supermassive black holes. Unlike stars or planets, black holes do not emit light that we can observe directly, but their gravitational influence is profound. When stars orbit a black hole, especially 1 millions or billions of times the mass of our Sun, their trajectories can become highly elliptical, erratic, and warped compared to standard Keplerian paths. These gravitational effects create orbital patterns that are unpredictable without taking the intense warping of spacetime into account. In particular, stars near the center of our own Milky Way provide a dramatic example. At the heart of the Milky Way lies Sagittarius A*, a supermassive black hole whose existence was confirmed by tracking the orbits of stars whipping around an otherwise invisible point in space. These orbits show extreme precession, acceleration, and deviation from simple ellipses, a dance governed not by classical gravity alone but by the extreme physics of general relativity. These stars serve as some of the best laboratories for studying how non-Keplerian orbits behave under the influence of an immense, invisible mass. In even more extreme environments, such as the vicinity of merging black holes, spacetime itself becomes so distorted that traditional orbital mechanics completely break down. In these regions, objects follow chaotic, spiraling paths dictated by the curvature of spacetime, leading to gravitational waves, ripples in the fabric of space and time that can be detected across vast cosmic distances. The observation of gravitational waves by LIGO and Virgo has opened yet another window into the study of invisible mass and non-Keplerian orbits. These waves carry with them detailed information about the masses and movements of the objects that created them, offering new and profound evidence of gravitational dynamics that go far beyond Kepler's classical vision. Even at smaller scales, non-Keplerian orbits can manifest in fascinating ways. Artificial satellites orbiting Earth, for instance, experience deviations from perfect Keplerian motion due to a variety of invisible influences, including atmospheric drag, radiation pressure from the Sun, the uneven distribution of Earth's mass, known as its gravitational field anomalies, and the gravitational tug of the Moon and other planets. These factors require constant adjustments and corrections to satellite orbits, showing that even in our own cosmic backyard, real-world orbits are rarely simple. At a planetary scale, moons and asteroids also provide evidence of non-Keplerian dynamics. Many asteroids, for instance, exhibit non-uniform orbits because of the Yarkovsky effect, a tiny force exerted when the asteroid absorbs sunlight and re-emits it as heat. Though small, this effect can cause significant changes in an asteroid's path over millions of years, resulting in trajectories that deviate from what Kepler's laws would predict. Such discoveries underscore the principle that whenever unseen forces act upon an orbiting body, whether those forces are massive like dark matter or subtle like thermal radiation, the resulting path will differ from the pure ellipses envisioned centuries ago. Looking even further into the future, understanding non-Keplerian orbits around invisible masses is not just an academic pursuit. It has practical implications for humanity's ambitions in space exploration. As we plan missions to other planets, asteroids, and potentially even interstellar voyages, accounting for these complex gravitational environments becomes critical. Future spacecraft may have to navigate regions where gravitational forces are heavily influenced by invisible masses, requiring new techniques in navigation and propulsion. Concepts like gravitational slingshots, currently used to accelerate probes, will need to evolve to consider these hidden influences, ensuring mission success in the complex gravitational seas of the universe. The interplay between light, matter, and gravity in these contexts also inspires new technologies on Earth. The mathematics developed to understand non-Keplerian orbits finds applications in fields like GPS navigation, deep space communications, and even predicting weather patterns. Thus, the pursuit of understanding invisible masses and their influence on orbits reverberates far beyond theoretical physics, touching aspects of everyday life in ways most people never realize. Yet perhaps the most profound implication of non-Keplerian orbits is what they reveal about the nature of reality itself. If most of the universe's mass is invisible, if the paths of stars, galaxies, and cosmic structures are governed by forces we cannot directly see, then our understanding of existence must stretch beyond the immediately observable. We are participants in a cosmic drama shaped by actors cloaked in darkness, moving according to laws that challenge our deepest intuitions about space, time, and gravity. The quest to understand these hidden dynamics pushes humanity toward new frontiers of thought and discovery. With every new observation, with every star whose orbit twists unexpectedly, with every gravitational wave captured from merging black holes, we peel back another layer of the cosmic veil. It is a pursuit that demands the fusion of imagination and precision, of dreams and mathematics, as we strive to map a universe where much of the mass, and much of the story, remains unseen. Furthermore, when multiple massive objects, such as clusters of black holes or dense stellar remnants, coexist in close proximity, their gravitational fields intertwine and create an intricate and dynamic gravitational landscape. Objects moving through such regions experience constantly shifting gravitational pulls, resulting in orbits that are chaotic, precessing, and sometimes completely destabilized. These environments create a perfect setting for non-Keplerian motion, where the simple elegance of elliptical orbits is replaced by a complex ballet of gravitational interactions. The study of such regions not only helps us understand the behavior of matter under extreme conditions but also serves as a natural laboratory for testing the predictions of general relativity. According to Einstein's theory, the fabric of space-time itself is curved by mass and energy, meaning that in regions with concentrated invisible mass, the trajectories of objects will naturally deviate from the classical paths expected under Newtonian gravity. Observations of stars orbiting near black holes, or gravitational waves generated by the mergers of such objects, provide compelling evidence that these relativistic effects are real and measurable. Another intriguing aspect of non-Keplerian orbits around invisible masses arises in the concept of rogue planets, planetary bodies that do not orbit a star at all but instead drift through interstellar space. Some of these planets may have been ejected from their native systems through gravitational interactions with massive, unseen companions. In these cases, the gravitational forces from hidden masses drastically alter what would have been a stable orbit into a chaotic trajectory, ejecting the planet into the dark void of space. The existence of rogue planets hints at a broader, unseen dynamism within galaxies, where not all mass is accounted for by visible structures. It is plausible that many more objects, stars, planets, entire solar systems, could be influenced or displaced by the gravitational pull of invisible masses, contributing to the complex gravitational architecture of galaxies that we are only beginning to comprehend. On even grander cosmic scales, entire galaxies themselves appear to engage in non-Keplerian motion when viewed within the large-scale structure of the universe. Galaxies are not stationary. They move through space, drawn by the gravitational influence of other galaxies, galaxy clusters, and even more enigmatic structures like the Great Attractor, a mysterious region of immense gravitational pull that seems to be dragging entire clusters of galaxies towards it. What makes this motion particularly fascinating is that much of the mass responsible for these large-scale movements cannot be directly observed, suggesting once again the presence of vast amounts of invisible matter. This phenomenon implies that the orbits of galaxies within clusters, and even the motion of galaxy clusters themselves, do not follow simple elliptical orbits around a visible center. Instead, their trajectories are complex, often influenced by massive structures hidden from direct observation. The cosmic flow patterns, as mapped by projects like the Cosmic Flows Surveys, reveal an intricate web of movements that defy the straightforward predictions of Keplerian dynamics. Instead of moving neatly around a central point, galaxies stream along the filaments of the cosmic web, pulled by the hidden mass concentrations that structure the universe at the largest scales. Adding to the mystery, observations of phenomena like the bullet cluster have provided some of the clearest evidence that visible matter and dark matter can behave differently during colossal cosmic collisions. In the bullet cluster, two galaxy clusters collided, and while the hot gas, the visible matter, slowed down and heated up due to the collision, the bulk of the gravitational mass, inferred from gravitational lensing, passed through almost unaffected. This separation between visible matter and gravitational mass offers a rare glimpse into the independent behavior of dark matter and reinforces the idea that invisible masses play a fundamental role in governing non-Keplerian orbital dynamics across the cosmos. The future of understanding non-Keplerian orbits around invisible masses lies in the development of increasingly sophisticated observational tools and theoretical models. Next-generation telescopes like the James Webb Space Telescope, the Vera C. Rubin Observatory, and upcoming gravitational wave observatories promise to reveal even finer details about the hidden architecture of the universe. By capturing the faintest distortions of light, the subtlest shifts in stellar positions, and the most delicate ripples in spacetime, these instruments will allow scientists to map invisible masses with unprecedented precision. As data pours in from these new observatories, researchers are likely to uncover even more exotic forms of non-Keplerian motion, potentially driven by forces and structures that are currently beyond our imagination. Some theories speculate about the existence of massive primordial black holes, remnants from the earliest moments after the Big Bang, scattered throughout the universe and influencing the motion of stars and galaxies in subtle but measurable ways. Others propose the existence of entirely new forms of matter or fields that could alter gravitational interactions at cosmic scales. At the cutting edge of this exploration are simulations of cosmic structure formation, where supercomputers model the evolution of the universe from the Big Bang to the present day. These simulations incorporate dark matter, dark energy, and complex gravitational interactions to recreate the large-scale patterns we observe in the cosmos. They reveal a universe shaped not by visible stars and galaxies alone, but by an intricate and unseen scaffolding of invisible mass, guiding the motion of everything from tiny planets to colossal galaxy clusters. The story of non-Keplerian orbits around invisible masses is a story of humility and wonder. It reminds us that what we see is only a fraction of what exists. It urges us to look deeper, to question our assumptions, and to embrace the profound complexity of the cosmos. It teaches that the universe is not a clockwork mechanism of predictable motions, but a dynamic, evolving, and deeply mysterious realm where unseen forces shape the destiny of all matter. As we continue to probe the invisible, we are not merely filling in gaps in our knowledge. We are expanding the very horizons of what it means to understand reality. Each discovery challenges us to think bigger, to accept that the universe is more intricate and interconnected than our ancestors could ever have imagined. In the grand dance of celestial bodies, it is often the unseen partners, the invisible masses and hidden forces, that lead the steps. Some theories propose that the observed non-Keplerian motions are not solely the result of unseen matter but instead hint at the need for a modification of gravity itself. One prominent idea is MOND, or modified Newtonian dynamics, which suggests that at extremely low accelerations, such as those found at the edges of galaxies, gravity behaves differently than Newton predicted. In the MOND framework, the gravitational pull does not diminish with distance in the expected way, leading to the flat rotation curve seen in galaxies without invoking dark matter. Although MOND has had some success in explaining certain galactic dynamics, it struggles to account for phenomena on larger scales, such as galaxy cluster dynamics and the cosmic microwave background patterns. Nevertheless, its existence emphasizes the deep uncertainties that still surround the exact causes of non-Keplerian orbital behavior. Whether the answer lies in invisible mass or a fundamental revision of gravitational laws remains one of the most profound questions in modern astrophysics. Adding yet another layer to this enigma are the findings from simulations of cosmic structure formation. When researchers modeled the universe assuming only visible matter and Newtonian gravity, the results failed to match the observed universe. Galaxies form too slowly, structures are too small, and the large-scale filamentary web of matter does not emerge. However, when dark matter is included, an invisible scaffolding upon which normal matter gathers, the simulations produce structures strikingly similar to what we observe. This strongly implies that non-Keplerian motion, driven by unseen mass, is woven into the very fabric of cosmic evolution. One particularly captivating idea is the possibility that dark matter itself might clump into structures called dark stars or dark planets, composed entirely of dark matter particles. If such objects exist, they would exert gravitational forces without emitting any light, creating perfect candidates for inducing non-Keplerian orbits in nearby objects. These theoretical dark objects would behave much like regular celestial bodies in terms of their gravitational pull. But because they would be made entirely of dark matter, they would not emit detectable electromagnetic radiation. Their gravitational influence could disturb the orbits of stars, planets, and other objects nearby, causing their paths to deviate from what traditional Keplerian models would predict. The detection of such objects, however, remains an ongoing challenge. Since dark matter does not interact with light, our current observational techniques are ill-suited for spotting these enigmatic bodies directly. Instead, scientists rely on indirect methods, such as gravitational lensing or the study of motion in star clusters, to infer their presence. While these methods have been successful in revealing large-scale dark matter distributions, identifying individual dark matter objects remains a tantalizing frontier in astrophysics. Another possible source of non-Keplerian orbits around invisible masses could be black holes, particularly those that are stellar mass or intermediate in size. These black holes are often hidden within the dense environments of star clusters or within the cores of galaxies. When objects like stars or gas clouds interact with these black holes, they can be flung into erratic orbits or even ejected from the system entirely. Such orbits would deviate from the regular, predictable paths of planets around stars, particularly when the black hole's mass is concentrated in a small region of space, creating intense gravitational forces. These disruptions would lead to orbits that can shift over time in ways that are not accounted for by traditional Keplerian mechanics. What makes these non-Keplerian orbits around black holes especially fascinating is their ability to warp space-time itself. Einstein's theory of general relativity predicts that massive objects, like black holes, warp the fabric of space-time around them. This warping causes the paths of nearby objects to bend, and the closer an object gets to the event horizon of a black hole, the more dramatic these distortions become. For stars or gas clouds orbiting near a black hole, the very concept of a stable orbit is shattered. Instead of following predictable elliptical paths, these objects may experience sudden shifts in trajectory, precessing or spiraling inwards toward the black hole over time. The study of such orbits not only deepens our understanding of black holes but also provides a window into the nature of spacetime itself. By carefully observing the movements of stars in close proximity to black holes, astronomers can test the limits of general relativity and explore potential deviations from known gravitational laws. For instance, if we were able to observe a star that is orbiting just outside the event horizon of a black hole, we might uncover evidence of phenomena that challenge our current understanding of physics, such as quantum gravitational effects. These extreme environments where non-Keplerian orbits are most prevalent are also key targets for future astrophysical research. Instruments like the Event Horizon Telescope, which produced the first-ever image of a black hole's event horizon, will continue to advance our ability to study the behavior of objects near black holes. In the coming decades, observations of gravitational waves, ripples in spacetime caused by the acceleration of massive objects like colliding black holes, will also provide further insight into the dynamics of non-Keplerian motion. The detection and analysis of these waves allows scientists to directly observe how the fabric of spacetime is warped by invisible masses. But while black holes and dark matter are prime candidates for explaining non-Keplerian orbits, another fascinating possibility is the influence of exotic gravitational phenomena, such as those predicted by theories like string theory or quantum gravity. These theories suggest that spacetime itself may be far more complex than our current models allow. String theory, for example, posits the existence of extra dimensions beyond the familiar three of space and one of time. In such a framework, the presence of unseen dimensions could lead to gravitational effects that cannot be explained by classical physics. If additional dimensions exist, they may affect the motion of objects in ways that we cannot currently observe with our standard methods. Non-Keplerian orbits could emerge as a consequence of interactions between the familiar four-dimensional spacetime and these extra dimensions. This might open the door to entirely new forms of motion, governed not by the familiar forces of Newtonian or even Einsteinian gravity, but by yet undiscovered forces that operate on a level beyond our understanding. Furthermore, one of the more mind-bending aspects of non-Keplerian orbits is the potential involvement of hypothetical objects such as primordial black holes or strange matter. Primordial black holes, which may have formed in the early universe from fluctuations in the density of matter, could be scattered throughout space, undetectable by conventional means. If these objects exist, their gravitational pull could disrupt the orbits of nearby stars, planets, and even entire galaxies, leading to non-Keplerian motion in unexpected places. Similarly, strange matter, composed of hypothetical particles that differ from normal matter, could have unique gravitational properties that cause objects to move in ways that are not predicted by current models. In the quest to understand non-Keplerian orbits, the role of computer simulations becomes increasingly important. Advances in computational astrophysics allow researchers to model the gravitational interactions of billions of particles, simulating the motion of stars, planets, black holes, and dark matter under a variety of conditions. These simulations not only help us predict the motion of objects in complex systems, but also allow scientists to test different theoretical models. By comparing simulated results with real observations, researchers can refine our understanding of gravity and the unseen masses that influence the cosmos. Simulations have already revealed surprising results, such as the discovery of dark halos, of dark matter surrounding galaxies. These halos, which are invisible in optical wavelengths but detectable through their gravitational effects, may contain vast amounts of unseen mass that dictates the motion of stars and gas clouds. As simulations become more detailed and more capable of modeling complex gravitational interactions, they may offer clues to other forms of invisible mass and further illuminate the nature of non-Keplerian orbits. While much of the scientific community focuses on unraveling the mysteries of dark matter and black holes, an equally crucial area of study is the interaction between non-visible mass and visible matter. How do invisible masses like dark matter interact with ordinary matter? What is the true nature of dark energy, the enigmatic force accelerating the expansion of the universe? Answers to these questions will not only clarify the nature of non-Keplerian motion but also provide deeper insights into the fundamental forces that govern the universe at all scales. The search for invisible mass and its effects on orbital motion represents a convergence of astrophysics, cosmology, and particle physics. It challenges our understanding of gravity, mass, and the very fabric of space-time. Every new discovery brings us closer to understanding not just the mechanics of the universe, but the very nature of reality itself. Non-Keplerian orbits remind us that the universe is far more complex than our early models predicted. The gravitational dance of celestial bodies is not a simple, predictable march of planets and stars around the center of mass. Instead, the unseen forces, dark matter, black holes, and perhaps entirely new gravitational effects, add layers of complexity to this cosmic choreography. Each new breakthrough in our understanding of these orbits is a step toward unlocking the deeper secrets of the cosmos, a journey that promises to reveal not just the hidden masses shaping the universe but the hidden laws that govern all of reality. The pursuit of understanding non-Keplerian orbits around invisible masses is not just about explaining the behavior of individual stars or galaxies. It is also about uncovering the fundamental mechanics of the universe itself. At the heart of these investigations lies a profound question: what is the true nature of the forces that govern the motion of celestial bodies? The discovery of non-Keplerian orbits, particularly when driven by unseen forces such as dark matter or the warping of spacetime around black holes, suggests that our understanding of gravity and mass is incomplete. As researchers delve deeper into these mysterious phenomena, they are forced to consider that there may be hidden layers of complexity that traditional physics cannot fully explain. While Newton's laws and Einstein's theory of general relativity have revolutionized our understanding of gravity, the presence of dark matter, black holes, and other exotic cosmic objects points to gaps in our current models. Theoretical physics, in turn, is expanding into new frontiers, including attempts to unify gravity with quantum mechanics, which could hold the key to resolving these mysteries. One of the most pressing challenges is determining whether the anomalies observed in non-Keplerian orbits are the result of new physics, or merely the product of phenomena we have yet to fully observe. While dark matter is currently the leading explanation for the unseen mass affecting orbital motion, it is not the only candidate. Some scientists propose that the effects could be due to modifications of gravity at large scales, a theory that could explain certain cosmological observations without the need for invisible matter. These alternative models challenge not only the nature of gravity but also the assumptions we've made about the fabric of spacetime. The discovery of gravitational waves, ripples in spacetime caused by the acceleration of massive objects, has also opened up a new avenue of exploration in the study of non-Keplerian orbits. When two black holes or neutron stars collide, they send out gravitational waves that travel across the universe, carrying with them valuable information about the extreme environments in which they were generated. These waves provide a direct glimpse into the dynamics of invisible masses, offering a new perspective on how objects in orbit interact with each other and with unseen forces. In recent years, the detection of gravitational waves has become one of the most exciting developments in astrophysics. Observatories like LIGO, Laser Interferometer Gravitational Wave Observatory, and Virgo have opened a new window into the universe, enabling scientists to study the behavior of black holes and neutron stars in ways that were previously impossible. These observations not only confirm the existence of invisible masses such as black holes but also provide insights into their gravitational effects, further enhancing our understanding of non-Keplerian orbits. As more gravitational wave events are detected, scientists hope to map the distribution of these invisible objects throughout the universe. By studying the orbits of black holes and other compact objects, researchers can learn more about the invisible structures, such as dark matter halos, that influence their motion. This data could lead to breakthroughs in our understanding of how galaxies form, how dark matter interacts with normal matter, and how the universe evolved from a hot, dense state to the vast, complex structure we observe today. Meanwhile, the hunt for dark matter continues to drive much of the research in this field. Despite the fact that dark matter has not yet been directly detected, its gravitational influence on visible matter is undeniable. In galaxy clusters, for example, the motion of galaxies and gas clouds suggests the presence of unseen mass that cannot be accounted for by ordinary matter alone. Similarly, the formation of large-scale cosmic structures, the webs of galaxies that stretch across the universe, requires the existence of a massive, invisible component that helps to bind the visible matter together. One of the most promising ways to detect dark matter is through the study of gravitational lensing. This phenomenon occurs when light from a distant object, such as a galaxy or a quasar, passes near a massive object, like a galaxy cluster or a dark matter halo, and is bent by its gravitational field. By carefully observing these distortions, scientists can map the distribution of dark matter in the universe. This technique has already revealed the presence of large-scale dark matter structures, offering indirect evidence of the unseen mass that shapes non-Keplerian orbits. In addition to dark matter, researchers are also investigating the role of dark energy in influencing the motion of galaxies and the expansion of the universe. Dark energy, which is believed to make up around 68% of the universe, is a mysterious force that is driving the accelerated expansion of the cosmos. While its exact nature is still unknown, its gravitational effects could play a role in the evolution of cosmic structures, potentially influencing the orbits of galaxies and other large-scale phenomena. The search for answers to these cosmic mysteries requires a combination of advanced observational techniques, theoretical models, and powerful computational tools. With the advent of new telescopes, such as the James Webb Space Telescope, which is capable of observing distant galaxies in unprecedented detail, scientists are poised to make new discoveries that could shed light on the nature of non-Keplerian orbits and the unseen forces that drive them. In the coming decades, the study of non-Keplerian orbits is likely to become one of the most important areas of research in astrophysics. The mysteries surrounding dark matter, black holes, and other invisible masses are intricately linked to our understanding of the universe as a whole. By studying the motion of stars, galaxies, and other celestial bodies, we can learn not only about the objects themselves but also about the fundamental laws that govern the cosmos. At the same time, the exploration of non-Keplerian orbits offers a unique opportunity to test the limits of our current physical theories. As we probe the behavior of objects in extreme gravitational environments, we may uncover new insights into the nature of space, time, and the forces that shape the universe. The study of non-Keplerian orbits is not just about understanding the motions of distant objects, it is about uncovering the very essence of reality itself. This journey into the unknown promises to be one of the most exciting and rewarding scientific endeavors of the 21st century. As new discoveries unfold, we will continue to push the boundaries of human knowledge and redefine our understanding of the universe. And, just as with the great scientific revolutions of the past, the answers we find may not only solve the mysteries of non-Keplerian orbits, but may also open the door to entirely new realms of discovery, fundamentally altering the way we view the cosmos. The quest to understand non-Keplerian orbits around invisible masses is a journey that reveals much about the fundamental workings of the universe, not only in terms of celestial mechanics but also in our broader understanding of the nature of reality. As scientists dive deeper into these uncharted territories, they continue to challenge the limits of human knowledge and the very frameworks that have served us for centuries. The question of what is out there, beyond the visible stars and galaxies, pushes the boundaries of our comprehension. As the study of non-Keplerian orbits progresses, one of the most intriguing developments is the increasing realization that our universe may operate under rules far more complex than previously imagined. For decades, physicists have assumed that gravity, as outlined by Isaac Newton and Albert Einstein, was the governing force for the motion of celestial bodies. But with the discovery of mysterious objects and phenomena, such as dark matter and dark energy, scientists are rethinking everything from the basic nature of gravity to the structure of space-time itself. The advent of new technologies has played a pivotal role in this evolution of thought. Space telescopes, such as the Hubble Space Telescope, along with ground-based observatories, have allowed astronomers to peer deeper into the cosmos than ever before, revealing anomalies in the motion of celestial bodies that don't quite align with Kepler's laws. These discrepancies have prompted the introduction of new concepts in theoretical physics, many of which suggest that there are unseen forces and masses at play in the universe, forces that, for now, defy our understanding. In particular, black holes, which have long fascinated scientists and the public alike, offer a prime example of these hidden influences. While black holes are known to have massive gravitational fields, their effects are not always predictable in traditional models. For example, when observing the orbits of stars around a supermassive black hole, astronomers have found that they don't follow the expected patterns based on Kepler's laws of motion. These non-Keplerian orbits are often attributed to the immense gravitational forces that warp space and time, creating orbits that are anything but elliptical. The study of these objects, especially the supermassive black holes at the centers of galaxies, has led to profound insights into the fabric of space itself. The way these orbits behave under the influence of such intense gravitational fields is reshaping our understanding of general relativity. Einstein's theory of gravity, which has been the cornerstone of our understanding of how massive objects interact, may need to be updated or expanded to fully account for these new phenomena. The challenge, however, lies in figuring out what these updates might look like. As more is understood about black holes, it becomes apparent that the universe's most extreme environments may hold the key to unraveling the mystery of non-Keplerian orbits. For instance, the study of gravitational waves, first detected in 2015, has provided a novel way of exploring these phenomena. Gravitational waves are ripples in space-time caused by the acceleration of massive objects, such as when two black holes collide or when a neutron star merges with another object. These waves carry information about the objects that produce them, allowing scientists to study their properties without directly observing them. With the growth of the field of gravitational wave astronomy, new opportunities arise to probe the behaviors of these unseen masses. Gravitational waves offer a direct glimpse into the motions of invisible objects and the influence they have on the surrounding space-time. This could lead to an entirely new understanding of the invisible forces at play, beyond dark matter and black holes. These new methods of detection are pushing the boundaries of observational astronomy and offering unprecedented insights into the mechanics of non-Keplerian orbits. In tandem with gravitational wave research, astronomers are also making use of increasingly sophisticated simulations to model the behaviors of non-Keplerian orbits. These computer simulations incorporate general relativity and other advanced theories to predict how objects move in the presence of invisible masses. The results of these simulations often reveal behaviors that cannot be accounted for by Newtonian physics, or even by Einstein's theories alone. By comparing these simulations with real observations, scientists can refine their understanding of how the universe works on both large and small scales. This process of comparison between theory and observation is at the heart of modern scientific inquiry. In the past, many of the greatest discoveries in physics came from the realization that the theories we had been relying on were incomplete. Just as Newton's laws were replaced by Einstein's theory of relativity, our current understanding of gravity and motion may be just the beginning of a much larger and more complex picture. As more data is collected and new observations are made, the theories we hold may evolve or give way to entirely new concepts. One of the most exciting aspects of these investigations is the realization that we may be on the verge of discovering entirely new forms of matter or forces that exist in the universe. While dark matter has been the leading candidate for explaining non-Keplerian orbits, scientists are beginning to explore other possibilities, including the existence of exotic matter or even new dimensions of space and time. These possibilities are not just theoretical speculations but have the potential to be tested with future experiments and observations. As we continue to delve into the mysteries of non-Keplerian orbits, we are not just answering questions about individual celestial objects, but also uncovering the deeper truths about the universe itself. By exploring the behavior of stars, galaxies, and other cosmic entities under the influence of invisible masses, we gain insights into the fundamental forces and structures that govern the cosmos. These discoveries challenge the limits of human knowledge and invite us to reconsider our place in the vast expanse of the universe. In the decades to come, the study of non-Keplerian orbits will likely remain one of the most profound and exciting frontiers in astrophysics. With each new discovery, we are not just learning more about the universe, we are pushing the boundaries of what is possible to understand. As scientists continue to unravel the secrets of invisible masses and their effects on the orbits of celestial bodies, we can only imagine how these discoveries will shape our understanding of the cosmos and our place within it. As we delve deeper into the study of non-Keplerian orbits, the significance of the invisible forces at play becomes increasingly evident. Understanding how masses, that are not directly visible, influence the motion of objects within their gravitational reach not only expands our knowledge of celestial mechanics, but also forces us to reconsider what we thought we knew about the fundamental workings of the universe. These investigations have already led to major shifts in astrophysics, with researchers acknowledging that invisible masses, like dark matter and dark energy, are just the beginning of a far more intricate cosmic puzzle. One of the biggest challenges that researchers face when studying these orbits is the sheer complexity involved in detecting and measuring the influence of invisible masses. Unlike planets or stars, which emit light or other detectable radiation, invisible masses like dark matter don't interact with electromagnetic radiation in the same way. They remain undetectable through conventional telescopes, which are designed to observe light or other forms of radiation. This means that, in many cases, scientists must rely on indirect methods to infer the presence of these invisible masses. One key approach involves the observation of gravitational lensing, a phenomenon predicted by Einstein's theory of general relativity. Gravitational lensing occurs when light from a distant object is bent as it passes near a massive object, such as a galaxy or a cluster of galaxies. This bending of light can create distorted or multiple images of the background object. By studying these distortions, scientists can map out the distribution of mass, including invisible mass, in the intervening object, providing valuable clues about the unseen components of the universe. Gravitational lensing has already been instrumental in revealing the presence of dark matter in galaxy clusters, but it also plays a crucial role in the study of non-Keplerian orbits, helping astronomers infer the presence of invisible masses that exert influence on celestial bodies. Another method that has proved invaluable in studying invisible masses and their gravitational effects is the use of advanced simulations. These computer models, which integrate general relativity and other cutting-edge theories, allow scientists to simulate how matter behaves under the influence of invisible forces. The results of these simulations can then be compared to real-world observations, revealing discrepancies that point to the presence of unseen objects or forces. For example, simulations of galaxy formation often predict the presence of dark matter in certain regions, explaining the observed gravitational effects on the motion of stars within galaxies. By refining these simulations with more accurate data, researchers are steadily inching closer to a more complete picture of the universe's unseen components. In addition to dark matter, there are other candidates for invisible masses that could be influencing non-Keplerian orbits. One such possibility is the existence of primordial black holes, which are theorized to have formed in the early universe. Unlike the black holes we typically observe, which form from the collapse of massive stars, primordial black holes would have formed during the high-energy conditions of the Big Bang. These objects would be much smaller than typical black holes but could still exert significant gravitational influence on nearby objects. The challenge, however, lies in detecting them, as their size and mass make them difficult to differentiate from other forms of dark matter. Nonetheless, the possibility that primordial black holes could be contributing to non-Keplerian orbits remains an active area of research. While dark matter and primordial black holes are the most commonly discussed invisible masses in the context of non-Keplerian orbits, another fascinating possibility is the existence of exotic forms of matter or even entire new dimensions of space. These concepts, which emerge from certain interpretations of string theory and other cutting-edge models of physics, suggest that the universe may contain hidden forms of matter or energy that we have yet to detect. In these models, the presence of invisible masses could be due to new, exotic particles or fields that interact in ways that are fundamentally different from the matter and energy we are familiar with. These possibilities challenge our current understanding of physics and open the door to a deeper exploration of the nature of the universe. As scientists continue to explore the implications of non-Keplerian orbits, they are also discovering that the effects of invisible masses may be more widespread than previously thought. For instance, some studies suggest that the gravitational influence of dark matter could extend far beyond individual galaxies, potentially affecting the motion of entire galaxy clusters. This idea has led to the development of the concept of dark matter halos, large, diffuse regions of dark matter that surround galaxies and clusters. These halos could play a critical role in the formation and evolution of galaxies, influencing how they interact with other galaxies and how they develop over cosmic time. Another area of research that has gained significant attention is the study of gravitational interactions between non-visible objects, such as the interactions between dark matter and ordinary matter. Although dark matter does not emit light, it does exert gravitational influence, and scientists have begun to investigate how this influence might affect the distribution of stars and other objects within galaxies. Some researchers have even proposed that dark matter could be responsible for the observed missing mass in galaxies, where the gravitational effects on the motion of stars cannot be fully explained by the visible matter alone. By studying these interactions, scientists hope to uncover more clues about the nature of dark matter and its role in shaping the universe. In addition to dark matter, dark energy, the mysterious force that is driving the accelerated expansion of the universe, is another invisible component that may be influencing non-Keplerian orbits. Although the precise nature of dark energy remains one of the greatest mysteries in physics, it is believed to play a significant role in the large-scale structure of the universe. As scientists explore the behavior of non-Keplerian orbits in distant galaxies, they are beginning to consider the possibility that dark energy could be affecting the motion of objects on cosmological scales, influencing the way galaxies and galaxy clusters interact. Understanding how dark energy interacts with both visible and invisible matter could provide crucial insights into the future of the universe itself. The exploration of non-Keplerian orbits has also led to exciting developments in the field of astrophysical theories. As researchers push the boundaries of our understanding, they are uncovering new and unexpected results that challenge established ideas. For example, the study of orbits around supermassive black holes has raised questions about the validity of our current models of gravity, particularly in extreme environments. These investigations have prompted some scientists to consider modifications to general relativity that could better account for the unusual motions of objects in such intense gravitational fields. Some theories even suggest the possibility of a new, fundamental force that operates alongside gravity, potentially offering a more complete description of the forces at play in the cosmos. As these ideas continue to evolve, the implications for our understanding of the universe are profound. If new forces or dimensions of space are discovered, they could reshape our understanding of everything from the formation of galaxies to the fundamental laws of physics. The study of non-Keplerian orbits, then, is not just an academic exercise. It is a window into the deepest mysteries of the cosmos, a journey that could ultimately transform the way we perceive the universe and our place within it. As we continue exploring the unknown regions of non-Keplerian orbits, we enter a realm where our current understanding of physics faces its greatest challenges and potential breakthroughs. The very nature of these orbits demands that we reevaluate the foundational principles that govern celestial mechanics, gravitation, and motion. Unlike the predictable and well-understood Keplerian orbits, which are governed by the direct gravitational pull of visible masses, non-Keplerian orbits occur in situations where invisible forces, such as dark matter or dark energy, dominate. These invisible forces don't just affect the trajectory of orbiting bodies. They may also alter the fabric of space-time itself. The implications of these findings reach far beyond simple curiosity. Understanding non-Keplerian orbits could unlock entirely new aspects of physics, revealing interactions and forces that challenge not only how we view gravity but how we conceptualize the universe. For example, as researchers explore the effects of invisible masses on planetary orbits and the motion of stars, they are forced to consider theories that go beyond Newtonian mechanics and Einstein's theory of general relativity. While these theories have been extremely successful in explaining the behavior of objects within our solar system, they may fall short in extreme environments, such as the centers of galaxies or near supermassive black holes. This has led to the proposal of modifications to general relativity, such as theories involving extra dimensions, quantum gravity, or alternative gravity models that could better account for the complexities observed in non-Keplerian orbits. One of the most intriguing developments in this field is the growing evidence of non-Newtonian gravitational effects at large scales. Observations of galaxy clusters, the cosmic microwave background radiation, and the motion of galaxies themselves suggest that gravity behaves differently than we expect when dealing with large, distributed masses. In particular, the apparent discrepancies in galaxy rotation curves, where the outer regions of galaxies rotate much faster than predicted by the visible matter alone, cannot be explained by Newtonian gravity or general relativity without invoking the presence of dark matter. This observation points to the idea that invisible mass is distributed in a way that affects the gravitational dynamics on a cosmic scale, influencing not only the motion of galaxies but the structure of the entire universe. The study of non-Keplerian orbits has also revealed that there may be more complex interactions between visible and invisible masses than we originally anticipated. While dark matter and dark energy have long been theorized to exist, their exact nature has remained elusive. Yet, through the study of orbits around invisible masses, scientists have been able to make significant strides toward uncovering the properties of these enigmatic components of the universe. One particularly promising avenue of research is the idea that dark matter may not be a uniform substance but could have different properties depending on its location in space. For instance, certain regions of space may contain more dark matter, while other areas could be relatively devoid of it. This uneven distribution could explain some of the observed anomalies in orbital dynamics, such as the accelerated rotation of galaxies or the bending of light and gravitational lensing. In parallel to these advances, scientists are also beginning to investigate how non-Keplerian orbits can be used as tools for exploring the nature of the universe's most mysterious objects, black holes. The complex motions of objects orbiting supermassive black holes, especially in the centers of active galaxies, provide valuable insights into the behavior of gravity in extreme environments. These orbits, often erratic and seemingly unpredictable, suggest that our current models of general relativity may need further refinement to account for the behavior of objects under such intense gravitational influences. For example, some researchers propose that the motion of these objects could be explained by the presence of additional, hidden forces that interact with ordinary matter in ways that are not fully understood. The study of non-Keplerian orbits also plays a crucial role in the search for new types of celestial bodies that may be invisible to traditional observational methods. While we often think of objects like stars, planets, and black holes as being the primary players in gravitational interactions, there are many other potential candidates for invisible mass that could influence the orbits of nearby objects. For instance, primordial black holes that formed in the early universe, could be scattered throughout the cosmos, exerting subtle gravitational influences on the motion of stars and galaxies. These objects are difficult to detect, as they do not emit light or radiation, but their gravitational effects could reveal their presence. The potential discovery of primordial black holes would not only provide further evidence for the existence of non-visible mass, but could also offer a new avenue for testing and refining our models of gravity. In addition to primordial black holes, researchers are also exploring the possibility of hidden dark matter structures, such as dark matter halos, which could be responsible for the gravitational anomalies observed in non-Keplerian orbits. These halos, which are thought to surround galaxies and galaxy clusters, may harbor large amounts of invisible mass that can affect the motion of stars, gas, and other visible matter. By studying the motion of objects within these halos, scientists hope to gain a deeper understanding of the distribution of dark matter and its role in shaping the evolution of galaxies and other cosmic structures. This research also has the potential to reveal entirely new forms of matter or energy that have yet to be discovered. As we continue to investigate the effects of invisible masses on non-Keplerian orbits, it becomes increasingly clear that these orbits are not just anomalies to be explained away but rather represent an essential piece of the cosmic puzzle. They challenge our assumptions about the nature of gravity, space-time, and the fundamental forces of the universe. More importantly, they offer us a glimpse into a deeper, more complex reality, where unseen forces shape the motion of everything from stars to entire galaxies. The study of non-Keplerian orbits, therefore, is not just a scientific curiosity, it is a crucial step in unlocking the secrets of the universe itself. To understand the significance of non-Keplerian orbits, it is important to dive deeper into the conceptual shift that these orbits bring to our understanding of gravity. For centuries, Kepler's laws and Newtonian mechanics governed our view of orbital motion. We understood how planets moved around stars, how moons orbited planets, and even how artificial satellites could orbit Earth. The simplicity of these laws made it seem like the universe's motions were relatively straightforward. However, as scientists began observing more complex systems, such as galaxy clusters and the interaction of dark matter, the assumptions of Keplerian orbits began to unravel. In these large-scale systems, objects did not obey the tidy patterns predicted by Kepler's laws. For instance, galaxy rotation curves, specifically the fact that galaxies rotate faster than would be expected from the visible matter, took scientists by surprise. This phenomenon, once thought to be an anomaly, ultimately led to the theory of dark matter. It was postulated that galaxies had massive amounts of invisible, non-luminous matter exerting gravitational influence, even though we could not observe it directly. The motion of stars within these galaxies was no longer easily explained by visible matter alone, forcing scientists to reconsider the fundamental laws that describe orbital motion. Dark matter, while a dominant force in non-Keplerian orbits, is not the only factor that could alter traditional orbital dynamics. Other factors, such as the influence of nearby supermassive black holes or the gravitational pull of other galaxies, could also create complex, non-elliptical orbits that defy classical expectations. In these cases, objects like stars and gas clouds orbiting these gravitational anomalies can follow curved, chaotic, and unpredictable paths that appear completely detached from the smooth, elliptical trajectories predicted by Keplerian theory. The very nature of these orbits requires modifications to our models of space-time and gravitation. These modifications may not only enhance our understanding of how gravity works but could also lead to new discoveries that push the limits of modern physics. One of the most intriguing aspects of studying non-Keplerian orbits is how they reveal gaps in our knowledge of the universe. While Keplerian orbits provide neat solutions to the motions of celestial objects under the influence of known gravitational forces, non-Keplerian orbits present new and puzzling questions. For example, the motions of stars near supermassive black holes defy expectations, suggesting that there may be additional forces at play. We see this most clearly in the study of the orbits of stars around the supermassive black hole at the center of our galaxy, Sagittarius A star. The stars orbiting this black hole move in ways that seem to break the typical rules of gravity. They follow curved paths that are influenced not only by the black hole's gravitational pull but also potentially by unseen sources of mass or energy, further complicating our understanding of orbital mechanics. Scientists have long known that supermassive black holes exert tremendous gravitational influence. However, the orbits of stars near these black holes reveal new, unexpected behaviors. Some of these stars are moving at speeds that are so high, they should escape the black hole's gravitational pull. Others move in unpredictable ways, and some even appear to follow paths that suggest the presence of forces we cannot yet measure. These anomalies have prompted the suggestion that the standard laws of gravity might need to be adjusted to account for these extreme environments. Such revelations push us to rethink the foundations of physics itself. Moreover, these non-Keplerian orbits offer clues about the nature of dark energy, a mysterious force responsible for the accelerated expansion of the universe. The evidence for dark energy has been mounting for decades, and its influence is becoming more apparent in the motions of galaxies and clusters of galaxies. Like dark matter, dark energy is invisible. It does not emit light or radiation that we can observe directly. However, it seems to have a gravitational effect on the large-scale structure of the universe, altering how galaxies interact with each other, and influencing the rate at which the universe expands. In the context of non-Keplerian orbits, dark energy could provide the missing piece of the puzzle, explaining why certain objects behave in ways that defy traditional gravitational theories. One of the key ways in which non-Keplerian orbits can shed light on dark energy is by observing the orbits of objects within galaxy clusters. These clusters are often surrounded by massive, invisible halos of dark matter. Within these halos, the gravitational influence of dark matter distorts the orbits of galaxies and their constituent stars. Similarly, the motions of galaxies within these clusters can provide important clues about the nature of dark energy. If dark energy is influencing the trajectories of objects at large scales, its effects could be detected by observing the movement of galaxies in non-Keplerian orbits. As we continue to gather more data, it's likely that we will discover new ways to detect and understand dark energy, potentially unlocking the secrets of the universe's accelerated expansion. The concept of non-Keplerian orbits also connects with the idea of gravitational waves, ripples in spacetime caused by the acceleration of massive objects. While gravitational waves are typically associated with the violent motion of black holes or neutron stars, they can also be influenced by the motion of objects in non-Keplerian orbits. In particular, when two massive objects are in close proximity, the distortion of spacetime created by their movement can lead to the generation of gravitational waves. These waves carry information about the nature of the objects involved and the forces acting upon them. By studying gravitational waves, scientists can learn more about the underlying dynamics of non-Keplerian orbits, further expanding our understanding of how invisible masses interact with visible matter. As researchers continue to study the complex dynamics of non-Keplerian orbits, they are also refining their techniques for observing distant objects in the universe. The advancement of telescopes and observatories, such as the Hubble Space Telescope, the James Webb Space Telescope, and ground-based observatories, has made it possible to detect increasingly faint objects and phenomena. These instruments allow scientists to probe deeper into space, observing stars, galaxies, and other celestial bodies that were once invisible to us. By tracking the orbits of objects in these distant regions, we are gradually uncovering the subtle effects of invisible masses on their motion, providing a richer, more detailed picture of the universe. The future of studying non-Keplerian orbits lies in the combination of theoretical modeling and observational astronomy. As scientists develop new models of gravity and refine their understanding of dark matter, dark energy, and gravitational waves, they will be able to make more accurate predictions about the behavior of celestial bodies in non-Keplerian orbits. These predictions can then be tested by observing the orbits of objects in distant galaxies, black holes, and other exotic systems. With advancements in technology and the continued expansion of our knowledge, we are poised to make groundbreaking discoveries that will reshape our understanding of the cosmos. As we continue to explore non-Keplerian orbits, it's crucial to examine how these dynamics could reshape not only our theoretical understanding of astrophysics, but also practical applications in fields like space exploration and navigation. While non-Keplerian orbits were once a phenomenon relegated to the study of galaxies and dark matter, the growing precision of space telescopes and sensors means that the concept is becoming more relevant in the context of spacecraft navigation as well. As we venture further into the cosmos with missions designed to explore distant planets, moons, and even asteroids, understanding the peculiarities of these orbits will be paramount for ensuring the success of such expeditions. For instance, consider missions that target regions influenced by supermassive black holes or regions that may harbor dark matter. Understanding the gravitational anomalies caused by these invisible masses will allow mission planners to devise more accurate trajectories for spacecraft. The traditional, simplified orbital models may no longer suffice, as they fail to account for the complexities of these objects and their influence on the spacecraft. Non-Keplerian orbit theory provides a more detailed framework for understanding the forces at play in these extreme environments. Navigating through such regions requires new methodologies for path calculation, which might include adjustments based on predicted gravitational disturbances or even the indirect influence of unseen energy sources. One of the most exciting possibilities in the study of non-Keplerian orbits comes from the potential applications to interstellar travel. While we have yet to develop the technology for practical interstellar exploration, non-Keplerian orbits could play a crucial role in designing efficient routes to distant star systems. Traditional orbital mechanics, based on Kepler's laws, often work well for systems within our own solar system. However, if we wish to travel outside this region, to stars far beyond, we need to account for the gravitational effects of unseen masses and energies. These may not be immediately obvious in the physical sense, but could create distortions in spacetime that influence the trajectory of spacecraft. This is where the study of gravitational anomalies, linked to non-Keplerian orbits, comes into play. A spacecraft on an interstellar journey would need to adjust its path regularly to account for unforeseen gravitational influences, such as the interactions with dark matter or the pull of distant, invisible celestial bodies. The subtle distortions in the fabric of spacetime, influenced by invisible forces, may not always be noticeable at first but could slowly accumulate over the course of a long journey, necessitating sophisticated models to account for them. This would also require advancements in the computational power necessary to calculate these new, more complex paths, essentially evolving navigation systems that can account for a broader range of forces. Another avenue worth exploring is the potential for non-Keplerian orbits to inform future missions focused on capturing or interacting with black holes. Black holes, particularly supermassive ones, continue to captivate the imagination of both the public and the scientific community. As we look to the future of space exploration, capturing data from black holes could reveal critical insights into how gravity operates at its most extreme levels. The orbits of objects close to these cosmic giants are complex and governed by forces we are only beginning to understand. The study of non-Keplerian orbits around black holes could yield insights into the relationship between visible and invisible mass, the nature of spacetime, and the mechanisms that drive the formation of such extreme objects in the first place. For example, the study of the orbits of stars near black holes could reveal more about the nature of accretion disks, the rotating masses of gas and dust that spiral into black holes. These orbits, influenced by the powerful gravitational fields of the black holes, can provide clues about the dynamics of material that falls into these cosmic voids. It is believed that as material spirals into a black hole, it heats up and emits radiation, which can be observed and studied. By observing the motion of objects near the event horizon, scientists can indirectly measure the properties of the black hole itself, its mass, spin, and even its potential to emit gravitational waves. Furthermore, the more we understand about non-Keplerian orbits, the better we can interpret observations made by telescopes focused on detecting gravitational waves. These waves are produced by the motion of extremely massive objects, such as colliding black holes or neutron stars. The study of how objects move in non-Keplerian orbits, especially in extreme gravitational fields, can provide insights into the types of events that produce gravitational waves. When two massive objects orbit each other in such close proximity, they can send ripples through spacetime that we can detect with observatories like LIGO and Virgo. The detailed study of orbital dynamics in extreme environments could help us understand how these objects behave before they collide, which would be crucial for predicting and interpreting gravitational wave events. Another fascinating possibility tied to non-Keplerian orbits is the concept of gravitational slingshots or assists. In space exploration, gravity assists are used to alter the path of spacecraft, using the gravitational pull of a planet or moon to increase the spacecraft's speed without expending additional fuel. These maneuvers, while currently used within our solar system, could potentially be adapted for use in interstellar travel as well. However, this would require a deeper understanding of how invisible forces, such as dark matter or energy, influence the gravitational fields of nearby objects. By mastering these principles, we could develop methods of using gravitational slingshots more effectively, opening up new possibilities for efficient space travel over vast distances. Additionally, the study of non-Keplerian orbits has implications beyond just theoretical astrophysics. It could help us refine our understanding of fundamental physics. At the heart of the study of non-Keplerian orbits lies the question of what governs gravitational forces on the largest scales. We know that gravity behaves in a predictable way under most conditions, but when it comes to the large-scale structure of the universe, things become less certain. As we probe deeper into the complexities of non-Keplerian orbits, we might uncover new theories of gravity that challenge or expand upon Einstein's general relativity. Einstein's general theory of relativity has been incredibly successful in explaining a wide range of phenomena, from the motion of planets to the bending of light around massive objects. However, its predictions are not always sufficient when it comes to explaining phenomena involving large-scale cosmic structures or the interaction of unseen forces like dark matter and dark energy. By studying non-Keplerian orbits, scientists may be able to refine or even revolutionize our understanding of gravity, possibly leading to a more unified theory that incorporates quantum mechanics alongside general relativity. Such a discovery would fundamentally alter how we view the universe and our place within it. As we continue to study non-Keplerian orbits, we are not just learning about distant galaxies and black holes. We are also deepening our understanding of the very fabric of the universe. Each new observation and discovery brings us one step closer to unraveling the mysteries of the cosmos. With continued advancements in observational tools and theoretical models, the exploration of these complex orbital dynamics will likely lead to even more profound insights into the nature of space-time, gravity, and the invisible forces that shape our universe. These journeys would not be simple straight-line paths but rather carefully calculated routes that account for hidden gravitational wells and energy fluctuations scattered throughout interstellar space. Furthermore, understanding non-Keplerian orbits could help scientists identify safe corridors for travel, regions where gravitational distortions are minimal and stable over time. Mapping these gravitational highways could enable spacecraft to conserve energy, using the natural contours of spacetime itself to assist in propulsion, a concept similar to the gravitational slingshot maneuvers already employed around planets, but on a much grander and more complex scale. Essentially, future space navigators might learn to ride the currents of gravitational fields shaped by both visible and invisible masses. The study of non-Keplerian orbits also has profound implications for the search for extraterrestrial life. Many exoplanets discovered so far orbit in regions where gravitational anomalies suggest the presence of massive, unseen structures. If these regions are rich in dark matter or influenced by exotic objects like rogue black holes, it could impact the potential habitability of nearby planets. Tidal forces, radiation levels, and orbital stability all hinge on the unseen gravitational landscape, meaning that understanding these orbits is essential for evaluating where life might exist beyond Earth. Additionally, non-Keplerian orbits offer insights into the life cycles of stars and the evolution of galaxies. In star clusters, for instance, the presence of invisible mass can influence stellar dynamics, affecting how stars are born, live, and die. In some clusters, stars exhibit motions that suggest gravitational influences beyond the observable mass, hinting at the presence of dark remnants like black holes, neutron stars, or concentrations of dark matter. Over billions of years, these unseen influences shape the structure and behavior of entire galaxies, meaning that understanding non-Keplerian orbits is crucial for building accurate models of galactic evolution. Beyond astrophysics, there is a philosophical dimension to the study of non-Keplerian orbits that touches on humanity's place in the universe. The realization that most of the gravitational forces shaping the cosmos arise from invisible entities challenges the assumption that reality is only what we can directly observe. It pushes us to develop tools, both technological and intellectual, that allow us to perceive and comprehend phenomena that exist beyond our immediate senses. This pursuit mirrors the broader scientific endeavor to uncover hidden truths and expand the boundaries of human knowledge. Moreover, the exploration of non-Keplerian orbits might eventually reveal new fundamental forces or particles. Just as the study of anomalies in planetary orbits led to the discovery of Neptune and later influenced the development of general relativity, so too might the unexplained behaviors observed today lead to breakthroughs in our understanding of dark matter, dark energy, or entirely new aspects of physics. The patterns hidden in the motions of stars, galaxies, and spacecraft could serve as subtle clues pointing the way toward revolutionary discoveries. Research into these orbits also intersects with the development of advanced computational models and simulations. Traditional Newtonian or relativistic models are often insufficient for accurately predicting the behavior of systems dominated by invisible mass. As a result, scientists employ complex simulations that incorporate not just gravity, but also quantum effects, space-time curvature, and the potential interactions of dark matter. These models require immense computing power and sophisticated algorithms, often pushing the limits of current technology and inspiring innovation in fields like artificial intelligence and machine learning. There is also an emerging interest in using non-Keplerian dynamics to design new types of artificial satellite orbits around Earth. These orbits, influenced by carefully applied forces such as radiation pressure from the Sun or electromagnetic effects, could enable satellites to maintain positions that would otherwise be unstable. For example, a spacecraft could hover at a fixed point in space without following a traditional elliptical orbit, opening up new possibilities for communication networks, Earth observation, and deep space gateways. Intriguingly, the principles learned from non-Keplerian orbits could be applied even further to the design of future space habitats and megastructures. Envision massive space stations or even entire artificial worlds positioned using non-Keplerian techniques, allowing them to remain stable in regions where traditional orbits would be impossible. These structures could serve as stepping stones for humanity's expansion into the solar system and beyond, providing vital hubs for exploration, research, and colonization. Even the methods by which we detect invisible masses rely heavily on the understanding of non-Keplerian motion. Techniques like gravitational lensing, where massive unseen objects bend the light of more distant stars and galaxies, depend on detecting deviations from expected trajectories. Similarly, the slight wobbles in the motions of stars can reveal the presence of orbiting exoplanets or hidden stellar companions, many of which exert their influence without emitting any light of their own. As we delve deeper into these mysteries, it becomes clear that non-Keplerian orbits are not just an oddity or an exception, they are a fundamental part of the cosmic tapestry. They represent the unseen architecture of the universe, the invisible scaffolding upon which galaxies, stars, planets, and life itself are built. To understand them is to unlock the secrets of existence on the grandest scale imaginable. Each new observation of an unexplained orbit offers an opportunity to test these theories, pushing the boundaries of our understanding even further. Non-Keplerian orbits thus act like a natural laboratory where nature itself experiments with forces we have yet to fully grasp. Observations that deviate from predictions compel us to rethink or expand our models, ensuring that the scientific pursuit remains dynamic and ever-evolving. In regions dominated by invisible masses, such as the cores of distant galaxies, studying non-Keplerian motion becomes even more crucial. Here, the stars whip around at speeds that should tear galaxies apart according to visible mass calculations alone. Yet galaxies remain intact, hinting at a hidden, stabilizing presence. Whether this stabilizer is dark matter or something even stranger remains an open question. Non-Keplerian orbital analysis is one of the strongest clues we have to uncovering what lies hidden in the deep fabric of the cosmos. In the context of our own Milky Way, non-Keplerian orbits have already led to groundbreaking discoveries. The orbits of stars close to Sagittarius A*, the supermassive black hole at the center of our galaxy, do not follow simple Keplerian predictions. Instead, they display peculiar precessions and accelerations that have allowed scientists to map the mass and size of the black hole with remarkable precision. Without the insights gained from studying these irregular orbits, our understanding of black holes would be far less complete. In satellite technology, the application of non-Keplerian orbit principles has begun to manifest in practical designs, especially with concepts like solar sails. These spacecraft use the gentle pressure of sunlight to maintain orbits that are not purely gravitational, allowing for stationary positions relative to Earth or other celestial bodies without expending fuel. Mastering these techniques could revolutionize communication networks, deep space exploration, and Earth observation platforms. Another exciting application involves the positioning of satellites at artificial Lagrange points, where the gravitational forces and orbital motion of a satellite, Earth, and the Sun balance out in a way that is not predicted by simple two-body Keplerian mechanics. These non-traditional orbits could serve as stable points for space stations, fuel depots, or scientific observatories, providing strategic advantages in the expanding human presence in space. Non-Keplerian orbits also have philosophical implications that challenge our deepest assumptions about the universe. They force us to confront the possibility that much of the cosmos is governed by entities we cannot see and perhaps cannot directly detect. The notion that entire regions of space behave according to the gravitational pull of unseen matter invites a profound sense of mystery and humility about our place in the universe. In the realm of computational astrophysics, simulating non-Keplerian systems presents unique challenges. Traditional simulation techniques, which often assume gravitational interactions based solely on visible mass, must be augmented with complex models that incorporate factors like dark matter distributions, relativistic effects, and time-dependent gravitational fields. The computational power needed to accurately model these systems is immense, pushing the limits of current technology and driving innovations in algorithms and supercomputing. Interestingly, non-Keplerian dynamics are not restricted to astronomical scales. Similar principles can sometimes be observed in microscopic systems governed by forces analogous to gravity, such as electromagnetic fields or fluid dynamics. By studying these analog systems in laboratory conditions, scientists hope to gain new insights into the behavior of non-Keplerian systems on a cosmic scale, forging a bridge between the very small and the unimaginably large. Understanding non-Keplerian orbits also enhances our ability to predict and interpret gravitational lensing events, where light from a distant source is bent around a massive object between the source and the observer. Deviations in the lensing pattern often hint at the presence of invisible masses that alter the expected paths of the light beams, offering another indirect method of probing the hidden mass of the universe. The field is ripe for future discoveries, especially as next-generation observatories like the Vera C. Rubin Observatory and the Nancy Grace Roman Space Telescope come online. These powerful instruments are expected to detect countless new examples of non-Keplerian orbital behavior, providing unprecedented data sets for analysis. Every new observation carries the potential to uncover hidden structures, new forces, or even entirely new forms of matter. As our observational capabilities improve, so too does our ability to refine theoretical models that attempt to explain these phenomena. Whether through modifications of existing theories, the proposal of new particles like WIMPs, weakly interacting massive particles, or the development of completely novel frameworks, the study of non-Keplerian orbits will remain at the forefront of scientific inquiry for decades to come. Ultimately, non-Keplerian orbits around invisible masses remind us that the universe is not a static clockwork mechanism governed solely by simple, predictable rules. Instead, it is a dynamic, evolving entity filled with mysteries that challenge our intellect and fuel our curiosity. The more we learn about these invisible influences, the more we realize how much remains hidden, waiting to be discovered by future generations of explorers and scientists. In deep space exploration, spacecraft like the James Webb Space Telescope operate near Lagrange points, locations where gravitational forces and orbital motion balance perfectly. While technically these points are derived from Newtonian mechanics, maintaining a stable presence at them involves continuous corrections that create unique non-Keplerian dynamics. Unlike simple orbits, these trajectories require careful adjustments based on the complex interactions between the spacecraft, Earth, and Sun. In practical terms, this means that spacecraft located at these Lagrange points don't follow the simple elliptical paths described by Kepler's laws. Instead, they experience subtle forces and corrections that keep them in stable positions relative to Earth, allowing for more efficient observation and data collection without frequent fuel consumption. The ability to harness these non-Keplerian orbits opens up new possibilities for future space missions, from astronomical observatories to interplanetary probes. Moreover, these Lagrange points and non-Keplerian paths are essential for long-term missions beyond Earth's orbit. The Moon's orbit, for example, isn't strictly Keplerian either. It's influenced by the gravitational tug of Earth, and any attempts to maintain a spacecraft in orbit around the Moon need to consider these perturbations. As we look to build bases on the Moon or send missions to Mars, non-Keplerian orbits offer critical strategies for stability and efficiency in the complex gravitational environment of the inner solar system. At even larger scales, non-Keplerian orbits are critical in explaining the behavior of galaxy clusters, where the movement of stars within the cluster deviates from the predictions made by simple Keplerian mechanics. Here, dark matter plays a crucial role, and the study of non-Keplerian motion is helping scientists refine their understanding of how this mysterious substance influences the structure and dynamics of galaxies and clusters of galaxies. As we move forward with the study of such phenomena, it's clear that these non-Keplerian orbits will continue to challenge our theories and expand the boundaries of modern astrophysics. Whether it's by exploring distant stars in our galaxy or mapping out the unseen structures of the cosmos, these orbits provide a window into the forces at work in the universe that we may not fully understand yet. The advent of advanced observational techniques, such as gravitational wave astronomy and ultra-high-resolution imaging from observatories like the Event Horizon Telescope, may soon provide us with more direct evidence of non-Keplerian orbits in action. These techniques allow us to peer deeper into space and observe phenomena that were previously invisible or too distant to detect, opening up new avenues for discovering the unseen masses and forces that govern the universe. In the near future, we may find that many of the objects we thought we understood, from exoplanets to black holes, reveal surprising behaviors that can only be explained by non-Keplerian dynamics. As our tools improve, we might discover that what we see is only the tip of the iceberg, with the majority of the forces and structures in the universe remaining hidden from view, waiting to be uncovered by the next generation of explorers and theorists. The study of non-Keplerian orbits around invisible masses is more than just an academic pursuit. It is central to unraveling the mysteries of the cosmos. Each new discovery and every new model we develop brings us closer to a deeper understanding of the hidden forces that shape the universe at every scale. From the smallest artificial satellites to the largest galaxies, non-Keplerian dynamics are providing the keys to unlocking the ultimate secrets of the universe. As we continue to explore the mysteries of non-Keplerian orbits, it becomes increasingly evident that these orbits hold profound implications for our understanding of cosmic structures. The path of objects moving under the influence of invisible masses is a reflection of the broader architecture of the universe itself. When we study how stars move in the outskirts of galaxies, or the strange orbits of objects caught in the gravitational grip of supermassive black holes, we begin to see that the universe is far more complex than traditional gravitational models would suggest. Consider the behavior of stars orbiting around supermassive black holes at the centers of galaxies. In many of these systems, the motion of stars does not conform to Kepler's laws, which assume a simple two-body interaction. Instead, stars exhibit behavior such as precession, where their orbits slowly twist over time, or even anomalous accelerations that suggest forces beyond the visible mass can influence their movement. Such dynamics can only be explained by invoking the presence of invisible masses, likely dark matter, surrounding the black hole. This kind of motion extends beyond the boundaries of our own galaxy, with large-scale structures such as galaxy clusters showing similar evidence of non-Keplerian dynamics. In these clusters, the observed motion of galaxies does not match the predictions made using visible matter alone. These clusters contain much more mass than we can observe, and it's the gravitational influence of this hidden mass that governs the motion of the galaxies within them. While dark matter is often proposed as the culprit behind these anomalies, it's possible that other unknown forms of mass or energy could be contributing to these effects, and studying non-Keplerian orbits helps us narrow down the possible causes. In addition to dark matter, the effects of general relativity play a crucial role in non-Keplerian orbits. While Kepler's laws assume a simple Newtonian framework, general relativity introduces the concept of curved spacetime. This means that the path of a moving object is not simply the result of gravitational attraction but also influenced by the warping of space and time around massive bodies. The strong gravitational fields near black holes and neutron stars can cause significant deviations from Keplerian expectations, leading to orbits that can only be described by Einstein's equations. In these regions, the influence of gravity is so intense that even light can be bent, leading to fascinating phenomena such as gravitational lensing. The study of non-Keplerian orbits has also spurred innovations in the field of astrophysical modeling. Traditional n-body simulations, which model the gravitational interaction between a collection of objects, often rely on the assumption of Keplerian dynamics. However, these models need to be updated to account for the additional complexities introduced by factors such as dark matter, black holes, and general relativity. Scientists are constantly refining their simulation techniques to ensure that they can accurately predict the behavior of celestial objects in these extreme environments. As computational power increases, these simulations become more detailed, allowing researchers to explore increasingly complex systems that were previously too difficult to model. Looking ahead, the future of studying non-Keplerian orbits will likely involve even more sophisticated tools and techniques. For instance, the advent of gravitational wave astronomy is providing new ways to observe the universe. Gravitational waves, ripples in spacetime caused by the acceleration of massive objects, can carry information about objects and events that are invisible to traditional telescopes. By studying the patterns of gravitational waves, scientists can gain new insights into the behavior of objects in non-Keplerian orbits, such as merging black holes or neutron stars. These observations may help clarify the role of invisible masses in shaping the motion of objects in the universe. Furthermore, the detection of exoplanets in unusual orbits, such as those in binary star systems or those influenced by the gravitational pull of a nearby giant planet, also provides valuable data that can challenge our current understanding of orbital mechanics. These non-Keplerian orbits could reveal new classes of exoplanets with unique atmospheric and environmental conditions, broadening our understanding of planetary systems and the potential for life elsewhere in the universe. In the realm of astrophysics, every discovery of a non-Keplerian orbit pushes the boundaries of what we know about gravity, motion, and the distribution of mass in the universe. Each irregular orbit is a puzzle piece, offering a clue that could eventually lead to a larger understanding of the fundamental forces that shape the cosmos. From studying the dance of stars around black holes to modeling the complex interactions of dark matter and galaxy clusters, these non-Keplerian orbits reveal a universe that is far more mysterious and intricate than we had ever imagined. At its core, the study of non-Keplerian orbits around invisible masses challenges our perception of the universe itself. The more we learn, the more we realize how much remains hidden from our eyes. While we may never fully uncover all the secrets of the cosmos, the pursuit of knowledge about these orbits is one of the most exciting frontiers in modern science. The journey to understanding the true nature of the forces at play in our universe is just beginning, and as we venture further into space and time, the discoveries we make may reshape our understanding of reality itself. The ongoing research into non-Keplerian orbits is also illuminating broader questions about the nature of the universe itself. As we probe the universe's hidden masses, such as dark matter and dark energy, we confront the limitations of our current understanding. Traditional gravitational models, based largely on Kepler's laws, were groundbreaking in their time, but they failed to account for the full complexity of cosmic dynamics. The introduction of non-Keplerian orbits forces us to reconsider not only our theoretical models, but also the fundamental principles of how gravity and mass interact at cosmic scales. These hidden forces, far from being obscure curiosities, have the potential to revolutionize our understanding of physics. The influence of invisible masses on orbiting bodies suggests that we are only scratching the surface of what we know about gravity. Non-Keplerian orbits are a reminder that there is much more to the universe than meets the eye. As astronomers refine their observations and models, they are uncovering layers of reality that challenge our perception of space, time, and even the fundamental forces that govern the cosmos. For example, the precise mapping of galaxy clusters has revealed that the mass of visible galaxies cannot explain their motion. This discrepancy has led to the development of the dark matter hypothesis, which posits that a large portion of the universe's mass is invisible to traditional telescopes. Non-Keplerian orbits in galaxy clusters provide key evidence for this invisible mass. Galaxies in these clusters move much faster than expected based on the visible matter alone, suggesting that the gravitational influence of unseen matter is at work. Understanding how non-Keplerian orbits behave in these environments could provide the critical insights needed to uncover the properties of dark matter, an elusive substance that makes up a significant portion of the universe's mass but has yet to be directly detected. At even larger scales, the interactions between galaxies and the mysterious force of dark energy further complicate our understanding of orbits. The expansion of the universe, driven by dark energy, causes distant galaxies to move away from us. This phenomenon, which was first discovered through the observation of redshift in the light from far-off galaxies, has profound implications for our understanding of cosmic dynamics. In regions where dark energy dominates, the motion of galaxies deviates from the simple models of gravitational attraction that Kepler's laws would suggest. These large-scale cosmic movements are governed by forces that we have yet to fully comprehend, and non-Keplerian orbits offer a window into how these forces might operate. Moreover, as our technological capabilities continue to grow, we are likely to discover even more exotic forms of non-Keplerian motion in the universe. For example, the study of binary star systems, where two stars orbit a common center of mass, often reveals complex behaviors that defy simple gravitational predictions. These systems can exhibit irregularities in their orbits due to factors such as tidal interactions, relativistic effects, and the presence of additional unseen objects, such as black holes or planets. By observing how stars move within these systems, astronomers can refine their models of non-Keplerian dynamics and gain a deeper understanding of the forces shaping their motions. The discovery of exoplanets in unusual orbits is another exciting development in this area. Planets that orbit their stars in ways that are inconsistent with Keplerian laws offer tantalizing clues about the broader dynamics of planetary systems. Some exoplanets have been found in highly elliptical orbits, or in orbits that are influenced by the gravitational tug of nearby stars or other planetary bodies. These systems challenge our current models of planetary formation and highlight the need for a more nuanced understanding of how planets and other celestial bodies interact. In the future, the study of non-Keplerian orbits may reveal entirely new types of planetary systems that we have yet to imagine. In the realm of space exploration, non-Keplerian orbits are already influencing the design of future missions. Space agencies are beginning to consider how non-Keplerian dynamics can be used to optimize spacecraft trajectories, reduce fuel consumption, and extend mission lifetimes. Solar sails, which use the pressure of sunlight to propel spacecraft, are a prime example of how non-Keplerian orbits can be harnessed for practical applications. By exploiting the constant, though weak, push of sunlight, spacecraft can achieve acceleration over time without relying on conventional propulsion methods. This could revolutionize long-duration space missions, allowing spacecraft to travel vast distances through the solar system and beyond, without the need for constant fuel resupply. As we explore further, the relationship between non-Keplerian orbits and the search for extraterrestrial life also becomes increasingly significant. The study of exoplanets, particularly those in unusual orbits, can provide insights into the potential habitability of other worlds. A planet's orbit influences its climate, the length of its seasons, and the stability of its environment, all of which are crucial factors for supporting life as we know it. By studying the orbits of distant planets, we can begin to assess whether these worlds might harbor the conditions necessary for life. Non-Keplerian orbits, particularly those influenced by interactions with other bodies, may result in more dynamic and diverse climates, which could be conducive to the development of life in unexpected ways. The exploration of non-Keplerian orbits also pushes the boundaries of our philosophical understanding of the universe. Traditionally, the laws of physics have been seen as fixed and unchanging, with the motions of celestial bodies following predictable patterns. However, the discovery of non-Keplerian dynamics forces us to confront the idea that the universe is far more unpredictable and complex than we once believed. This realization can be both humbling and awe-inspiring, as it reveals just how much there is still to learn about the forces that shape our cosmos. The study of non-Keplerian orbits is, in a sense, an ongoing journey into the unknown, one that constantly challenges our assumptions and deepens our appreciation for the intricacy of the universe. Looking ahead, the possibilities for future discoveries related to non-Keplerian orbits seem endless. With advances in both observational techniques and computational models, we are poised to uncover even more about the mysterious dynamics of the universe. Whether it's through the detection of new exoplanets, the study of galaxy clusters, or the refinement of spacecraft trajectories, the exploration of non-Keplerian orbits will continue to be a central focus of modern astronomy and astrophysics. As we push the boundaries of knowledge, we may uncover secrets that reshape our understanding of gravity, mass, and the very fabric of space and time. The road ahead is both exciting and challenging. But one thing is clear: non-Keplerian orbits are not just anomalies. They are essential to our understanding of the universe. By studying these irregularities and uncovering the forces that drive them, we are unlocking new avenues for exploration and discovery. From uncovering the nature of dark matter to understanding the dynamics of distant galaxies, non-Keplerian orbits hold the keys to some of the greatest mysteries of the cosmos. The ongoing exploration of non-Keplerian orbits is paving the way for the development of new models in both theoretical physics and applied astronomy. As scientists refine their methods of observing the universe, they are beginning to detect more subtle forms of motion that previously went unnoticed. For example, in the study of rogue planets, those that do not orbit a star but instead drift freely through the galaxy, scientists are encountering some of the most complex orbital behaviors yet observed. These planets do not follow the neat elliptical paths predicted by Kepler's laws but instead exhibit erratic, unpredictable trajectories, influenced by factors such as gravitational interactions with passing stars or dark matter. The behavior of rogue planets raises profound questions about the nature of planetary systems and their formation. How do these planets form in the first place? Why do some break free from their parent stars, embarking on erratic journeys through the galaxy? These questions are fundamental to our understanding of the life cycle of planetary systems, and studying the non-Keplerian orbits of rogue planets could hold the key to unlocking those mysteries. By analyzing the gravitational effects that rogue planets have on nearby stars and other objects, astronomers can learn more about the forces at play in these unusual systems. Beyond individual celestial bodies, the study of non-Keplerian orbits is also critical for our understanding of larger-scale cosmic phenomena. For example, the movement of entire galaxies and galaxy clusters is often far from the predictable, orderly motion that Keplerian orbits would suggest. The gravitational interactions between galaxies, particularly in dense regions of space such as galaxy clusters, can lead to chaotic orbital dynamics that challenge our traditional models of gravity. These chaotic movements can be driven by a range of factors, including the presence of dark matter, the gravitational influence of neighboring galaxies, and even the mysterious forces of dark energy. Recent research has shown that the motion of galaxies within clusters is significantly affected by dark matter. This invisible, yet incredibly massive substance does not emit light or energy, making it difficult to detect, but its gravitational pull is evident in the way galaxies move. Without dark matter, the galaxies and clusters would be moving far slower than they actually are, suggesting that there is far more mass in these clusters than we can see. The study of non-Keplerian orbits in these regions is helping scientists map out the distribution of dark matter, offering one of the few direct ways to detect this elusive substance. In addition to galaxy clusters, the study of black holes provides another fascinating avenue for exploring non-Keplerian orbits. Black holes are perhaps the most extreme objects in the universe, with gravity so strong that not even light can escape their grasp. However, the orbits of objects near black holes are not simple, elliptical paths as Kepler would have predicted. Instead, the intense gravitational fields around black holes lead to highly complex and often chaotic orbits. For example, the stars in the vicinity of supermassive black holes in the centers of galaxies move in highly elliptical, often precessing orbits, influenced by relativistic effects that cannot be explained by classical mechanics alone. The study of these relativistic orbits around black holes is revealing new insights into both gravity and the nature of space-time itself. Einstein's theory of general relativity predicted many of the effects observed around black holes, but the details of how space-time behaves near these objects are still not fully understood. Observing the non-Keplerian orbits of stars and gas clouds around black holes is providing critical data that could help scientists refine or even challenge our understanding of relativity. In particular, by studying the way orbits change over time, scientists can begin to probe the structure of space-time in extreme environments, pushing the boundaries of physics to their limits. Another area where non-Keplerian orbits are playing a significant role is in the study of gravitational waves. These ripples in space-time, first predicted by Einstein and confirmed by observation in 2015, are produced by the acceleration of massive objects, such as when two black holes merge. The orbits of objects that generate gravitational waves are often highly non-Keplerian, exhibiting complex behaviors that result from the interaction of strong gravitational forces. By studying the orbits of these objects before, during, and after a merger, scientists can gain valuable insights into the properties of space-time, the nature of gravity, and the fundamental forces of the universe. The detection and analysis of gravitational waves is a rapidly growing field in astrophysics, and the study of non-Keplerian orbits is at the heart of this research. Gravitational waves carry information about the motion of massive objects and can be used to probe some of the most extreme environments in the universe. By analyzing the signals produced by these waves, scientists can study the dynamics of black holes, neutron stars, and other exotic objects that produce complex orbits. As technology advances and more gravitational wave observatories are built, the potential for discovering new types of non-Keplerian orbits, and using them to unlock the secrets of the universe, is vast. The relationship between non-Keplerian orbits and the search for dark energy is also an exciting area of exploration. Dark energy, the mysterious force that is accelerating the expansion of the universe, remains one of the most perplexing aspects of modern cosmology. Its effects are observable on the largest scales, as distant galaxies move away from us at increasing speeds. However, the precise nature of dark energy and how it interacts with matter and spacetime is still largely unknown. Some scientists believe that the study of non-Keplerian orbits, particularly at the scale of galaxy clusters, may provide important clues about the properties of dark energy. Recent studies have suggested that dark energy may be influencing the motion of galaxies in ways that are not fully accounted for by traditional gravitational models. The expansion of the universe, driven by dark energy, could be responsible for the observed deviations from Keplerian orbits in large-scale cosmic structures. By studying how galaxies in different regions of space move, and how their orbits deviate from the predictions of Kepler's laws, scientists hope to gain a deeper understanding of dark energy and its role in shaping the cosmos. Looking toward the future, the study of non-Keplerian orbits holds the promise of unlocking some of the most profound mysteries of the universe. As our observational tools become more sophisticated, and our understanding of gravity and mass evolves, we are likely to encounter new and unexpected phenomena that challenge our existing models. Non-Keplerian orbits, in particular, are providing a valuable window into the hidden forces that govern the universe. Whether it's through the study of galaxy clusters, rogue planets, black holes, or gravitational waves, non-Keplerian dynamics are at the forefront of modern astrophysical research. The continuing exploration of these orbits is reshaping our understanding of space, time, and gravity. With each new discovery, we are moving closer to answering some of the most profound questions in science. What is dark matter? What is dark energy? How do galaxies, stars, and planets form and evolve over time? By delving deeper into the mysteries of non-Keplerian orbits, we are unraveling the very fabric of the universe itself. The path forward is both thrilling and uncertain. Each breakthrough in the study of non-Keplerian orbits opens up new questions and challenges our assumptions about the cosmos. But it is in these uncertainties that some of the greatest discoveries lie. As we continue to push the boundaries of knowledge, we are embarking on a journey of cosmic exploration that will ultimately reshape our understanding of the universe and our place within it. The investigation of non-Keplerian orbits doesn't only challenge our understanding of space-time on a theoretical level, but also opens the door to practical applications. The technology developed to study these phenomena has far-reaching consequences for how we explore the universe and how we might one day travel through it. For instance, the study of gravitational forces and orbital dynamics has given rise to improvements in satellite navigation systems, communication technology, and even space exploration techniques. As we refine our ability to predict and understand non-Keplerian motion, the possibilities for space exploration expand exponentially. In the realm of space travel, understanding non-Keplerian orbits could allow for more efficient travel routes in our solar system and beyond. Current space missions rely on the predictable, elliptical orbits described by Kepler's laws, but understanding how objects deviate from these paths could provide new strategies for interplanetary travel. It could lead to the development of advanced propulsion systems that account for the complexities of non-Keplerian orbits, allowing for faster and more efficient journeys through the cosmos. One of the most intriguing aspects of this study is the potential to navigate through the gravitational effects of invisible masses, such as dark matter or even rogue planets, without the need for direct observation. As we learn more about how these invisible forces influence nearby objects, we could develop technology that detects their effects indirectly. This could open up entirely new ways of interacting with the universe, from monitoring cosmic radiation patterns to mapping the unseen components of the universe in ways that were once thought impossible. Furthermore, by understanding the dynamics of non-Keplerian orbits, we are also improving our understanding of the potential dangers in space. Rogue asteroids, interstellar clouds, and other hazards could pose a threat to Earth and the rest of the solar system. By studying how these objects move, we could develop better methods for tracking and predicting their paths. Early detection of potentially dangerous objects in non-Keplerian orbits could give humanity a much-needed advantage in preparing for cosmic events that might otherwise be difficult to predict. Non-Keplerian orbits also have the potential to revolutionize our understanding of the structure and evolution of the universe itself. The presence of invisible masses, such as dark matter and dark energy, has already begun to change the way we think about the formation of galaxies, stars, and planetary systems. These invisible components exert gravitational forces that influence the motion of visible matter in ways that we are only beginning to understand. The study of non-Keplerian orbits offers a window into this hidden part of the universe, and could help scientists make new discoveries about how galaxies and other cosmic structures form and evolve. In particular, the study of galaxy clusters is benefiting from this shift in perspective. Galaxy clusters, massive concentrations of galaxies bound together by gravity, often display non-Keplerian motion due to the gravitational influence of dark matter. This motion can reveal key information about the distribution of dark matter and its role in shaping the large-scale structure of the universe. By analyzing the non-Keplerian orbits of galaxies within clusters, astronomers are piecing together a more accurate picture of how dark matter interacts with visible matter, providing a deeper understanding of the universe's composition and dynamics. As we continue to explore these uncharted areas of space, we are also learning more about the fundamental forces that govern the universe. The study of non-Keplerian orbits challenges our classical understanding of gravity and opens the door to new theories that could reshape our view of the cosmos. Some scientists believe that non-Keplerian orbits could even provide clues to the existence of new, undiscovered forces of nature. For example, some of the more extreme gravitational behaviors observed around black holes and galaxy clusters might be explained by forces that go beyond the four known fundamental forces: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. If these new forces are discovered, it would represent a major leap forward in our understanding of the universe. This shift in thinking also extends to our understanding of space-time itself. General relativity, which has been our best model for understanding the curvature of space-time under the influence of gravity, has already been tested in extreme conditions, such as near black holes and neutron stars. However, non-Keplerian orbits are pushing the limits of our understanding of relativistic effects. The study of these orbits might one day lead to a new, more complete theory of gravity, one that not only incorporates the known forces but also accounts for previously unexplained phenomena. There is also the possibility that the study of non-Keplerian orbits could lead to entirely new forms of energy or technology. Dark matter, in particular, remains one of the greatest mysteries of modern science. If researchers can understand how non-Keplerian orbits are influenced by dark matter, they might eventually unlock the secrets of this mysterious substance. Some theoretical models suggest that dark matter could be harnessed as a source of energy, though this is still a distant possibility. Nevertheless, as we continue to uncover the properties of invisible masses, new technologies and applications are likely to emerge. The study of non-Keplerian orbits is not just an academic pursuit. It has the potential to reshape how we understand the universe and our place within it. By observing how objects move under the influence of invisible forces, such as dark matter and dark energy, scientists are pushing the boundaries of our knowledge. Each discovery brings us closer to understanding the fundamental forces of nature and the very fabric of space-time itself. As we look to the future, the possibilities are endless. From improving our space navigation technologies to uncovering new fundamental forces of nature, the study of non-Keplerian orbits is a key to unlocking some of the most profound mysteries of the cosmos. As we continue to refine our observational tools and theoretical models, we can expect to see even more groundbreaking discoveries that challenge our current understanding of the universe. Through the study of non-Keplerian orbits, we are not only expanding the boundaries of science but also preparing for the next great leap in our exploration of the cosmos. This journey is far from over, and as we venture further into the unknown, we are bound to uncover even more astonishing truths about the universe. The answers to some of the most pressing questions in astrophysics may lie in the very orbits that deviate from the norm, the non-Keplerian paths that reveal the hidden forces shaping the cosmos in ways we have yet to fully comprehend. As our understanding of non-Keplerian orbits deepens, we find ourselves faced with questions that go beyond just the immediate observation of these orbits. What is the larger framework in which these phenomena exist? The discovery of such complex gravitational patterns doesn't just challenge our models of planetary motion. It suggests that we are beginning to glimpse a far more intricate and dynamic universe than we ever imagined. It's as if the rules we thought we understood have suddenly expanded to reveal a far broader and more complex picture of how celestial objects interact. One of the crucial breakthroughs in the study of these orbits lies in the advent of more powerful observational tools and technology. The advent of space telescopes such as Hubble and the upcoming James Webb Space Telescope has given scientists the ability to peer deeper into the universe than ever before. These technologies allow us to observe phenomena that were once hidden in the vastness of space. With these tools, we can not only observe non-Keplerian orbits, but we can also collect data on the gravitational effects of invisible masses, such as dark matter, and track their impact on the motion of visible objects. This has given rise to new models of galactic and planetary dynamics that go far beyond what Kepler and Newton could have imagined. One of the major consequences of these findings is that they could alter how we perceive the very architecture of galaxies. Galaxies are not static collections of stars. They are dynamic systems in constant motion, shaped by gravitational interactions that extend far beyond the visible matter we see. The study of non-Keplerian orbits within galaxies suggests that dark matter, which makes up the majority of a galaxy's mass, plays a central role in determining how galaxies evolve over time. The gravitational influence of dark matter could explain a range of phenomena that were previously difficult to reconcile, such as the rotation rates of galaxies and the structure of galaxy clusters. This new perspective could lead to a fundamental rethinking of how galaxies form and evolve, offering insights into one of the most enduring mysteries of modern astrophysics. Additionally, understanding non-Keplerian orbits offers us an important tool for studying black holes, one of the most enigmatic and extreme objects in the universe. Black holes, by their very nature, exert such intense gravitational forces that they warp the space-time fabric around them. Objects in the vicinity of a black hole experience non-Keplerian motion, especially as they approach the event horizon, the point beyond which nothing, not even light, can escape. The study of these extreme orbital dynamics provides insight not only into black holes themselves but also into the nature of space-time, gravity, and the fundamental laws of physics. Non-Keplerian orbits around black holes help astronomers test predictions made by general relativity and investigate how space-time behaves under extreme conditions. These findings could eventually lead to new insights into the nature of quantum gravity, an area of study that seeks to reconcile general relativity with quantum mechanics. As we expand our search into more distant reaches of space, the importance of non-Keplerian orbits becomes even more apparent. The study of these phenomena is integral to the search for exoplanets and other planetary systems beyond our own. While much of our knowledge of exoplanets comes from studying their transits across their host stars, there are other, more subtle ways in which we can detect these distant worlds. By studying the non-Keplerian motion of stars, caused by the gravitational influence of planets orbiting them, scientists can indirectly detect the presence of planets that would otherwise be impossible to observe. This technique, known as astrometry, is particularly useful when observing exoplanets that are too far away or too faint to be directly imaged. By tracking the tiny, non-Keplerian movements of a star caused by the gravitational pull of an unseen planet, astronomers can infer not only the presence of the planet but also its mass, orbit, and other key characteristics. Moreover, the study of non-Keplerian orbits could potentially lead to breakthroughs in space exploration technologies. As we look to the future, there is the tantalizing prospect that understanding these complex gravitational patterns might help us find more efficient ways to travel between planets, or even across stars. The gravitational dynamics of non-Keplerian orbits could be harnessed to develop advanced propulsion systems that allow spacecraft to take advantage of gravitational assists in entirely new ways. For example, rather than relying on traditional propulsion methods, spacecraft could use the gravitational influences of large, unseen masses to navigate more efficiently through space. This concept, known as gravitational slingshots or gravity assists, is already used in some missions, but a deeper understanding of non-Keplerian orbits could unlock entirely new methods of interstellar travel. In the quest for interstellar travel, it is possible that non-Keplerian orbits could provide the key to navigating the vast distances between stars. While current spacecraft rely on conventional propulsion methods that are limited by the speed of light, new models based on non-Keplerian dynamics might offer a way to achieve faster travel. If we can better understand how invisible masses affect the motion of objects in space, we could potentially create propulsion systems that tap into these effects, allowing for faster and more efficient space travel. The idea of harnessing the gravitational forces of dark matter or other invisible masses to propel spacecraft may sound like science fiction, but as our understanding of the universe grows, it becomes more and more plausible. The study of non-Keplerian orbits is also paving the way for breakthroughs in the search for extraterrestrial life. As we extend our search for habitable planets beyond the confines of our solar system, we are increasingly focused on finding planets that might harbor life. Non-Keplerian orbits could play a crucial role in identifying such planets. By studying the gravitational effects of distant stars and their planets, we can identify planets that might be located in the habitable zone, where liquid water could exist on their surfaces. These planets might not always follow traditional Keplerian orbits, but their non-Keplerian motion could provide valuable clues about their potential to support life. In addition to the search for life, the study of non-Keplerian orbits has the potential to yield discoveries in other areas of science, including physics and cosmology. Theoretical models of non-Keplerian orbits challenge our current understanding of fundamental physics, particularly the nature of gravity and the structure of space-time. By studying these orbits, we can test the limits of general relativity and potentially uncover new forces or particles that have yet to be discovered. These findings could lead to a deeper understanding of the universe and its underlying laws, offering new insights into everything from the behavior of black holes to the nature of dark energy. Ultimately, the exploration of non-Keplerian orbits represents one of the most exciting frontiers in modern science. As our observational tools improve and our theoretical models evolve, we will continue to uncover new mysteries about the invisible forces that shape the universe. Whether it is through the study of dark matter, the search for exoplanets, or the quest for faster space travel, non-Keplerian orbits will undoubtedly play a pivotal role in our journey to understand the cosmos. The more we learn about these unusual orbits, the more we begin to realize just how much there is still to discover in the vast, unexplored reaches of space. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.